Great. So shall I? Oh, brilliant. Someone has this recorded. Fantastic. Right. Welcome, everybody. We've already done this intro. We are without Brad DeLong. The idea was to have a roundtable about climate change and the perceptions of economic history within the context of a conference about modeling and modeling systems. I'm Judy Stevenson. I am moderating the session. I am an economic historian. I'm associate professor of the economics of the built environment at UCL. I look at labor markets and the construction industry in the very long run. The construction industry accounts for 40% of global emissions and 80% of fixed assets and 100% of our experience of climate, within a built environment, which triggers my interest in this topic. As an economic historian, I note that there are two ways that economic history and to one extent economics have dealt with this topic. The first is in the long run development of institutions, property rights systems and culture, which is a very well established way that economic history has perceived climate. The second is in the creation of long-run data sets along the lines of sort of Madison's national accounting and extensive econometrics and projections in that. I'm very much hoping that this session gives us a more developed view of that emergent field. I'm going to introduce you all one by one now, so we can sort of get going. Our first speaker today is Richard Tol, Professor Richard Tol, Professor of Economics at the University of Sussex, and Professor of the Economics of Climate Change at the Free University Amsterdam. He is among the top 100 economists and among the top 100 climate scholars in the world. The abstract for your paper is the recent reemergence in the public and academy of Malthusianism, millenarianism, and environmental determinism is without empirical support. Our format today is that you will speak for 15 to 20 minutes. We will take some quick Q&A, move on to the next paper, and then forge a discussion out of the papers that we share. Richard, may I invite you? Thank you.
Thanks. It's an honor and pleasure to be here. I changed the title of my talk to climate determinism. The content is mostly the same, but I thought this would better cover what I'm going to do. I have 15 minutes. It's a very large subject, so I'm going to necessarily be sketchy. The talk is based on two papers. One will appear in a book fairly soon, but is available as a working paper already. And the other paper should be available as a working paper in April. And essentially, I'm going to talk about the long-run influence on development from both a Malthusian and a Solovian perspective. There is a lot of doom and gloom about climate change in the public concern. And you see four examples here. Of course, in England, we have Extinction Rebellion, one of the main activist groups who claim that climate change is human extinction. You often see in demonstrations about climate and protests about climate and climate policy, young people holding up placards saying, "You'll die of old age, I'll die of climate change," which is not just limited to a few protesters. In a recent survey, 57% of young people think that humanity is doomed because of climate change. This was published earlier this year in Lancet Planetary Change. And it's not just the public that professes this particular sentiment, but it's also politicians who have picked this up. And the current president of the United States thinks that climate change is an existential threat to humanity. In the academic literature, we see a revival of environmental determinism. This is a recent paper in PNAS, where they claim that because of climate change, 1 to 3 billion people are projected to be left outside the climate conditions that have served humanity well over the past 6,000 years, suggesting that we'll be in trouble as a species. This is also true in some of the papers that pretend to be economics. What you're looking at here is a paper from 2015 by Marshall Burke, Solly Xiang, and Ed Miguel, where they project in gray what economic development would be without climate change, and then in red what it would be with climate change. And what you see clearly is a reversal of economic growth in many countries, and at the same time an acceleration of economic growth in other countries. These countries start shrinking, and these countries start growing much faster than they would be, and than they would without climate change, suggesting that climate change is a major, climate and climate change are major determinants of economic growth. And the question is, of course, how true, how credible is this? I'm going to look at 4 data sets. I'm going to look at a high data set of the number of people on the grid. I'm going to compare that to the climate data set of the Climate Research Unit. I'm also going to look at long-term economic growth according to the medicine database and the geographic, the spatial pattern of economic development according to the data from the Global Data Lab. But let's start with population. And this is where people are, or rather where people were 21 years ago, not on the map, but in climate space. And what you see is that humans are actually spread over a large range of temperatures, 50 degrees, as well as over a very large range up to from 0 to 8 meters of annual rainfall, which is quite an enormous range. 50 degrees Celsius is, of course, much larger, very much larger than the projected climate changes over this and the next centuries. So this is where people obviously can live. I'll talk about whether they thrive in a few minutes. So this is just the data. You can fit a complex hull around this and say, well, this is the climate space that humans can occupy. Now, this is for the recent past. If you go back, take the entire high data set, which goes back 12,000 years, we actually see that this is true throughout most of recorded history. In blue, you're looking at a situation 10,000 years before the birth of Christ, and in yellow, you're looking at the situation now. And the only major change in this period was the colonization of Bergen in Norway in the year 1128. So basically, we have occupied this climate niche throughout the last 12,000 years. The Xu paper that I mentioned before reaches its conclusion that so many people will be outside the historical niche because they focus not on where people live, but on where 95% of the people live. And that is the area that you see in blue here, which is much, much smaller than the green area, which is where all people live. The red area shows the available climates on planet Earth. And this immediately suggests that it's not so much that we are limited by heat, but rather that definitely in the dry parts of the planet, we have basically crept up to any climate that is available to us. It immediately suggests that, well, had there been hotter places on the planet, then we would have moved there too. It's simply that we couldn't because they were not available. It immediately pours cold water on the idea that heat is somehow a constraint on humanity. If we look at what happened over time, this is a complicated graph. Here, 10,000 BC is the optimal climate. It's essentially where human populations were at its most dense 12,000 years ago again in climate space. And you see that we're actually a heat-loving species, right? 23 degrees is 24 degrees is roughly our optimal temperature, or was our optimal temperature 10,000 years ago. This, of course, assumes a Malthusian model, right, where climate is interpreted as a technology, and this was the best technology available. But the other points that you see on the graph is the maximum population growth rather than the maximum population density. And what you see is that through the early history, we actually liked it even warmer. And it's only in the previous millennium that we started moving into colder places. And then only in very recent times, we started moving into the very dry places, that the desert actually became habitable to human beings. But all this, what you see is that actually we're all over the map. We are the sort of species that apparently can live anywhere within the available climate. If you then look at what fraction of the variance in human occupation can actually be explained by climate, what you see is that over this 12,000 period, in orange, you're looking at the R squared, in blue, you're looking at the world statistic, and the same picture emerges. Actually, climate has become less and less important in determining where do people live. So the notion that climate change, a little bit of climate change, recall we live in a climate in a temperature range that spans 50 degrees, the 2 or 3 degrees or maybe 4 degrees of warming would pose an existential threat to humanity is a very strange thing to say if you look at where do people actually live. At the moment, and as you see that because of technological development, presumably the effect of climate change, the influence of climate change has actually waned over the centuries and millennia. Now, this is where people live. Let's look at how people thrive economically. The red dots that you're looking at are the observations on a subnational level, so states, provinces, those sort of things. According to data from the Global Data Lab, again plotted against temperature. And what you see is a very widespread, a very low explanatory power of temperature. If you focus on the higher temperatures, you actually, in the tropical places, you actually find some of the poorest people, but also some of the richest people on the planet. Immediately suggesting that climate cannot be a major determinant of wealth. There does seem to be sort of a lower bound that you can place on development, that in colder places you would find fewer very poor people. Whereas in hotter places, you would find more of them. And this seems to be statistically significant and robust. The other relationship that I show is here in gray. And that is just a naive regression of development or wealth on, I should say not wealth, I should say affluence, on temperature. And you see, well, this relationship seems to be significant. However, if we condition regression on development in the previous period, then it disappears. Now, this is true for the year 2020 in the data that you're looking at here for the year 2020. The same is true if you take the medicine data set, which is not subnational but national, run the regression of per capita income on climate, you find a significant relationship. But if you then condition also on the previous observation of per capita income, then the relationship with climate simply disappears. That is true if you do it in the year 2020 for administrative reasons. It's true if you do it for countries in the year 2020. And actually, it goes back all the way to 1870, which is sort of the oldest data set for which we have a sufficient number of countries that you can actually run a regression like that. Yes, climate seems to have been important in 1870, but not if we can also condition on income in the year 1820. And this is, of course, very much reminiscent of the results that Darren Adjemoglu found and Marcella Aslan found, that once you condition on other things as well, the effect of climate on development simply disappears. It simply vanishes. It's simply not economically or statistically significant anymore. Now, problem with all this is the lack of data for older systems. So we can also correlate it. We can correlate climate with other things that we know determine development. So what you're looking at here is the start of democracy plotted against the temperature, and you can see there isn't a whole lot going on here. The reason that I plot democracy is, of course, not because democracy in itself is that important, but this is mostly to do with in a democracy you have less of arbitrary expropriation of property. You have security of property rights typically. And what you see, and this is typically thought as a major determinant of economic development, there is hardly any solid relationship with climate. The same is true for the start of the demographic transition. Another indicator that people use for lack of economic data as the start of economic development, that at the time when population started booming, created a labor surplus, and that stimulated economic growth. And that may explain in part the takeoff of economies in terms of economic development. If you plot the start of demographic transition against climate, then again, you find a very weak correlation. So to wrap up, I have 19 seconds left. Neither climate determinism nor neo-Malthusianism nor neo-millenarianism is supported by any data as far as I can see. This is, of course, not to say that climate change is not important. Climate change directly affects human mortality and morbidity. Climate change will drive other species to extinction, but Homo sapiens is not one of the species that you should worry about any extinction risk because of climate change. Climate is not a major determinant of economic development, which of course does not mean that climate change does not affect the economy, probably in a mostly negative way. But those effects are not nearly severe enough to reverse economic growth. That's all I wanted to say. Thank you for your attention.
Thank you, Richard. Have we any questions on content specifically before we get into the bigger questions in the discussion? Danila, your hand is up.
Question: how what's the accuracy of the data on recent decades on the effect of climate when we started feeling the global warming? So how precise are the data sets that you used, and can you actually conclude anything about the recent decades?
The issue is not accuracy of data there, Danila. I mean, climate data, weather data are reasonably accurate. Economic data are also reasonably accurate. for recent decades. Not very accurate, but reasonably accurate. And the problem with the data is that there is very little climate change in the data. What we see is a lot of weather variation, but very little climate change. And that immediately implies that a lot of the sort of recent empirical studies that you see that claim to be about the effect of climate change on economic activity of all sorts, right? Not just total economic growth or trade or labor productivity or mortality or morbidity or energy demand or agricultural production or all those things. Typically, these studies are about the effect of weather shocks on economic activity, not about climate change on economic activity. And the difference between climate and weather is that climate change and weather shocks is that climate change is something that happens slowly and is anticipated. If you don't anticipate climate change, then essentially you must have been living under a rock by now, right, for the last 30 years. Whereas weather shocks are unanticipated. And the difference then in technical terms is, of course, that weather shocks sort of tell you the short-run elasticity, the short-run sensitivity of economic activity to the weather, whereas what you're interested in climate change is the long-run elasticity. And we all know from economic theory that short-run elasticities and long-run elasticities are different things, right? That's why they have different names. And the main difference is that you can adjust the capital stock and you can adjust your technology and your institutions in the long run, but not in the short run. To put it prosaically, if it rains, what you can do is put up your umbrella, or you can close the floodgates if it pours, right? That's a short run response to a weather shock, whereas the long run response to an increase in rainfall is that you buy an umbrella and you build those floodgates. So the two are very, very different. And what we have learned from the recent outburst of empirical studies that claim to relate climate and economic activity really looked at weather and economic activity rather than a climate and economic activity. And the two are just very, very different, and you can't learn much from one for the other. So the issue is not availability of data in recent times or accuracy of data. The issue is that it's the wrong data. You simply do not have the data on what you're interested in.
Thank you, Richard. Other questions? Steve or Dan? Steve, you're on mute.
I'll leave mine for the main discussion.
Okay, thank you. Dan, have you got a question? You're on mute. 2 years into a pandemic. Do I have to say it again?
So, you know, it's an interesting view. You'll see that I differ, although but we'll get to that. It's interesting. I'm glad to hear you. I'm glad that our mutual friend or acquaintance, Michael Oppenheimer, introduced us, and you accepted the invitation to speak. So thank you, and we'll get into it.
Okay, one chair's technical question then. Richard, you brought a lot of data together, and then the point that you're making in the questions is that it's a misunderstanding of, a misinstrumentation that we really have, or a misunderstanding of variables in terms of the ways that others are modeling this. What do you think can be done in order to, if there is going to be advances in understanding, predicting what is going to happen, which we're all interested in, no matter what perspective we come from, what can be done in terms of educating scholars and the world, world more generally, to understand the difference between particular strains of, historical phenomena, in data? So I completely take on board what you were saying about the difference between weather shocks and climate, because a lot of epidemiologists, and long-run health scholars, were consulting on the pandemic, and they're like, well, yeah, but you're talking about plague like it's a kind of one-off event. It just, it's not a one-off event. So for a lot of scholars in health economics felt that they needed to make a distinction that they still don't understand has been made. Is there something we should be doing about educating people about variables and data and how they should be interpreted?
Well, yes, that's our job as referees and editors, right? To get this into people's heads. Unfortunately, this whole I mean, I've been in this climate game for 30 years now, and I recall in the early 1990s that there was a lot of emphasis on the difference between weather and climate among geographers and agronomists and engineers. And that took about 10 years for very senior people to essentially tell people, yes, weather is not climate, right? The problem in the economics literature at the moment is that very senior people are saying the opposite, that weather is climate, and have been for a while. And when I mean very senior people, I also mean people who control access to the top 5 journals. And you see a lot of this nonsense being published in top journals. And that, of course, encourages young people to also make this mistake, right? It's essentially been legitimized by some of the bigger names in economics, which is very unfortunate. So this essentially implies that, yeah, it will take another decade or two to get this out of people's heads, that really those two things are different. And that is best done by demonstration. One of the reasons that I accepted this invitation is that I'm actually much impressed by what Cliometrics is doing, that the availability of older data sets, or data sets, not all the data sets, but data sets that describe his economic history in more detail, I think is terribly important. Not just because then we have a wider variety of climates in our data set, which is what we're truly interested in, but also we have a much better grip on other things that affect economic development if you look at a longer period of time. So one of my hobby horses is the Ricardian method, where essentially people regress agricultural land values on climate and find there is a relationship. And they do that for the year 1980 or for the year 2000, and then they just swap time and space and assume that this relationship that holds over space also will hold over time. Which I think is a fairly ridiculous assumption, but it's been published in the American Economic Review, so who am I to protest, right? Because we now have longer time series on agricultural land values, and for England, for instance, we have it going back to the 13th century. You can actually show that, yes, there is this relationship, but this relationship is conditional on two things. One is technology, and what we've actually seen over the last 7 centuries in England is that technological progress has focused on improving conditions in the poorest agricultural lands rather than focusing on the best agricultural land. So the relationship between climate and agriculture actually flattens over time because of technological progress. But the other thing that you see in this data is that trade policy is terribly important. You see a very rapid shock you see a complete change in your parameter estimates around the time of the Napoleonic blockade and around the time of the repeal of the Corn Laws. That the relationship between climate and agriculture completely changes during those times. So I think it's terribly important to bring economic historians into this debate, just to show, to bring more data to bear on the problem, but also to bring other insights into this, that it's not just climate that is important, but other things are terribly important as well.
Thank you. Much to pick up on in later discussion. Okay. Daniela, one more question before we move on to Steve's presentation.
I wonder, Richard, if you think that the data you use and the data we have on climate is, well, kind of two-dimensional, one can say. It has precipitation, it has temperature, but it ignores other variables, such as, for example, ocean. Such as ocean acidification, which is a result of increased CO2 concentration in the atmosphere. So there might be other factors such as like intensity of winds, hurricanes, etc., which you can either consider climate or you can consider it a consequence of climate or climate change. And then the question becomes, does the data that we have actually somehow reflect or illuminate what is happening vis-a-vis these other variables and economics?
No, that's a good point and a point of major concern, right? It's not just temperature and rainfall that matters, and it's not just the annual average or the annual total that matters, right? But the distribution of rainfall over the year, the distribution of temperature over the year matters for certain things. But it's also insulation that matters, right? How much radiation do you get directly on your crops? Wind obviously matters, particularly very high winds matter. Ocean acidification may be a concern, but doesn't vary that much over time and over space yet. So that is very hard to bring in. Same for CO2 concentrations, right? They also directly matter for agricultural production. So yes, all these things should be brought into the analysis at some point. The issue with the other climate and weather variables is data availability. And another issue is just the sheer complexity of you have so many potential explanatory variables that it actually may overwhelm your empirical analysis. So that is why people tend to focus sort of on what they presume are the two main things, right? And it's mostly a presumption rather than an assumption that has been tested. And that is temperature and rainfall, but obviously that needs to be refined. One issue there, definitely, if you look at total economic activity or income, is that what other weather variables you would consider depends very much on the economic activity or the economic sector you're looking at. What matters for agriculture is not the same as what matters for energy demand, and so on and so forth. And therefore you go back to those broad indicators, temperature and rainfall, rather than looking at the more refined indicators, such as whether you had a frost last winter, which killed all the pests that might have eaten your wheat otherwise, right? And the pests that are relevant for wheat are different than the pests that are relevant for maize, and are different for the pests that are relevant for rice. So it gets very complicated, and the more detail you bring in, sort of makes sense if you're interested in a very specific economic activity, but makes less sense if you're interested in total economic activity.
Thank you. Yeah, good point. I think at this point we move on to Steve's presentation. Steve Keen is Distinguished Research Fellow at University College London. Best known for the book Debunking Economics, he's been a critic of both mainstream neoclassical and Marxian economics for 50 years. He developed the open source system dynamics program Minsky, with unique features to enable modeling monetary dynamics. Today's paper is about estimates by economists of trivial economic impacts from triggering numerous tipping elements in the Earth climate, such as losing the Atlantic meridional overturning circulation, cannot be reconciled with the scientific literature on tipping points and are based on transparently false empirical and theoretical methods. Steve, are you able to screen share, and can I hand over to you? Thank you.
Yes, you can. Okay. I want to start by comparing economists on one side of my screen to scientists on the other. And this is from a paper on tipping points, just very, as you can see, a 2021 paper in journal PNAS. Tipping points reduce global consumption per capita by about 1.4% upon 6 degrees of global warming. At the same time, a paper not considering specifically tipping points, also very, very recent paper, comes out and said mean losses from global warming of 4 degrees Celsius for 3.67 degrees of GDP. In other words, GDP will be, in 2100, will be 3.67% lower than it would be in the total absence of climate change because of a 4-degree level of warming. So fundamentally a trivial amount of change. If you extrapolated that in terms of an annual rate of growth, you'd be looking at a drop in the rate of per capita income growth of less than 0.1%. You couldn't measure it in the the accuracy of economic statistics. On the other hand, here are some scientists. This is Lenton, Stefan and all in a paper in 2019 saying tipping points are too risky to bet against. And as part of that, they claim that warming must be limited to 1.5 degrees Celsius, far below the numbers you can see on the left-hand side. Stefan in 2018 came out and said a planetary threshold for breakdown of the climate system as we understand it, the Holocene climate which humanity evolved, could be as low as 2 degrees Celsius above pre-industrial levels. And Hansen back in 2015 said that 2 degrees of global warming is highly dangerous. So it's a very, very different perspective between the two disciplines. And when you look at it now, finally, both sides are realizing just how different their analysis is. So Lenton and Siskar, writing back in 2013, said there is a huge gulf in the understanding of natural scientists have of tipping points and how economists represent them, climate catastrophes in their IAMs. Stern and Stiglitz came out with a paper just this year where they said there's an overwhelming consensus in the scientific community that differs markedly from IAMs. Now, is that sloppy thinking? Is it just that we have this touchy-feely attitude by scientists where they're worrying about who species we might leave at 3.5 to 4 degrees of warming, or have IAMs left something out or many things out of their analysis? Well, taking a look at the literature, it's emphatically the latter. The IAMs leave out virtually everything that matters in analysing climate change. And I want to take a look at that Dietz paper to give an idea of why. So this paper concluded that tipping points will reduce global consumption per capita by about 1.4% at global warming of 6 degrees Celsius increase in average global temperature, based on a second-order polynomial fit of the data, and I'll keep on coming back to that particular element. Now, the tipping points they were looking at, Arctic summer sea ice would be gone, Greenland would be going, West Antarctic by the time of the 2200 also going, the Atlantic meridional overturning circulation, which we call the Gulf Stream as well, gone, Amazon rainforest, gone, Indian monsoon, much more volatile, permafrost released, and ocean methane hydrates also released. Now, when you look at this on a map that scientists themselves did of the way in which one tipping point can trigger another, all these elements would be gone at the current global climate. And they didn't even include methane hydrates in their list because they didn't think they'd be tipped before 2100. So we're talking about a completely different global biosphere. Now, this reminds me, and rather more scarily than back then, of how economists missed seeing the financial crisis coming. If you're old enough to remember 2007, you remember that economists were saying what a great year 2008 was going to be. And then, of course, that's when the global financial crisis came along. Now, Robert Solow, who's one of a number of Nobel Prize winners, was invited to the US Congress to talk about why did the models not see the crisis coming? And he basically said that he just doesn't trust these models, even though he built part of the growth models that these models were based upon. He said, any proposition has to pass the smell test. Does it really make sense? And his opinion was that CSG models did not make sense. And he said, there's no doubt the advocates believe what they say, but they seem to have lost their sense of smell altogether. And I'm saying that applies in climate change analysis as well. A world which is 6 degrees warmer than now, in which there's no ice anywhere, where we lose all those huge elements of the climate, hasn't been seen for 40 million years, which is 40 times longer than the length of time that humans or human-like species have been on the planet. So imagine that you would just get a 1.4% fall in the economy from changing from the world we're in now to that world simply doesn't make sense. So the question is, what on earth led to these results? They must be wrong. And there's two possibilities. This was a meta study of papers in economic journals. So either the study's methods are wrong, or the individual tipping point papers must also be wrong. The situation part of it is definitely both. So let's take a look at how the meta study itself. They focused on economist papers alone, and it's justifiable to do that as an analysis. So when you look through, there's no real analysis of this. So we bring them all together. They found 52 papers, and they admitted they didn't cover one thing, which was non-market damages. So as an example of their methodology, I want to look at how did they cover non-market damages. So they included estimates of non-market damages, so damages to the environment that didn't turn up in goods and services, and analyzed that as a sensitivity analysis instead. And what they did to do that is they used the work of a model called MERGE, which was first written in 1995. Now, MERGE is what's called willingness to pay to value damages to the environment. And they started from the assumption that damages were quadratic. Now, why did they assume a quadratic function? There was no better reason whatsoever in the paper than if damages are quadratic, then all you need is one data point and you can fit the curve. And then to come up with the point, they said, well, the point is 2.5 degree increase in temperature will cause 2% damages to the environment. And the rationale here was, their justification was, there was no survey, no analysis of willingness to pay in any sense whatsoever. They simply said, well, at the moment, meaning about 1992, the United States devotes 2% of its GDP to environmental protection. So that justifies one of the two numbers they used. But the damage function they gave was damages to the non-market, to the environment will be 0.0032 times the change in temperature squared. And that led to the prediction that the environment wouldn't be completely destroyed until the increase in temperature was 17.68 degrees Celsius. If you run that quadratic through that point, that's the point at which that quadratic hits a value of 100. Now, Dietz and co, almost 30 years later, in analyzing tipping points, which was not included in man, reproduced this uncritically. They said delta T cat is a catastrophic parameter set to 17.68 from the assumption, and nothing other than an assumption, that economic losses rise quadratically and they're calibrated to a loss of 2% at 2.5 degrees warming. Now, this makes no sense. First of all, man predates any attempts to calibrate tipping points. It doesn't include tipping points itself. So how can you use its non-market function to provide a sensitivity check for a paper on tipping points, even if their analysis is reasonable? But it's not reasonable. First of all, the assumption that quadratic damages are quadratic is entirely arbitrary. There's no empirical or logical reason as to why that would be. And secondly, the figure they used, 2% damages, was justified by analogy to 1990s warming. The 2.5 degrees Celsius change in temperature was entirely arbitrary. They gave no justification for that whatsoever. Now, what if you try to make this temporally consistent? To say, well, if you used 2% environmental spending in the 1990s to give your estimate of willingness to pay, why not use the temperature in 1990s as well? And that would give you 0.5 degrees Celsius. So if you use the quadratic that way, you get a quadratic which is 0.08 times the change in temperature squared. Now, that generates a catastrophic temperature prediction, not of virtually 18 degrees Celsius, but 3.54 degrees Celsius. It's much closer to the level that scientists regard as being catastrophic. It's still a crazy function, and especially for emulating tipping points. You should not be using a quadratic for the simple reason that tipping points are below an acceleration at some point in the rate of change of a process, and the third derivative of a quadratic is 0. It simply can't be fitted. But they used a quadratic multiple times, even when it wasn't justified by the need to reproduce the 21 core studies they were looking at. They should have used a function like, for example, a logistic. Now, if you take a look at that and say, well, here's the logistic that will give you 100% damages at 3.54, which is consistent with that, empirical, temporally consistent quadratic. And it also gives you much lower damages at the moment than you get out of a quadratic prediction, even from the very, very low numbers that Dietz used it. Now, this is much more suitable for trying to model tipping points. It's far more consistent because it has varying higher order derivatives versus a zero derivative for the third order and above derivatives of a quadratic. And it gives you low initial damages and then a rapid acceleration at 1.5 degrees Celsius, which is the level that scientists see as critical. And that's why they come out and saying we must limit it to 1.5. This requires an emergency response. Now, and let's now take a look at the actual papers, or one of the papers. This is a paper on the AMOC by Anthoff, Estrada, and Toll, 2016, shutting down the thermohaline circulation. And that, for those who don't know, it is this huge circuit that links all the planet's oceans, and the upper element of that circulates in the Atlantic, we call the AMOC. Now, if the AMOC breaks down, there'll be no change in global temperature, but there'll be a hotter Europe and a colder equator, a hotter southern Europe as well. And the difference would be about a 5 to 10 degree fall in winter temperatures in southern Germany, for example. Now, Hansen looked at this in a very detailed model and said he found a 10 to 20% increase in wind speeds, which means a 1.4 to 2 times increase in the speed of storms. We're giving us superstorms. And when, so this is the sort of worry the scientists have. Now, a recent paper came out saying that the AMOC was actually slowing down, and Richard Toll reacted good. This is the tweet where it was first identified. And here is Richard down the bottom saying, that's good. Why did he say it's good? Well, he modeled the shutdown of the AMOC using FUND, which considers only natural temperatures. In the Dietz supplement, it says AMOC slowdown is expected to have physical effects other than temperature, such as precipitation, but these have yet to be incorporated in economic studies. So we have many global circulation models built by economists that are based on temperature and not based on precipitation. And the same thing is said by Anthoff and co. in this paper. They simply see the thermohaline shutdown as reduced warming. There's no consideration of what that change in warming might do to the level of precipitation. And the effects are therefore in large positive. Then the conclusion was that if we shut the AMOC down, global income will rise by 1.3%. And that was one of the papers taken by Dietz and incorporated in their results. That's the only one that they use. Now, there was an acknowledgement at the end of the paper that maybe things will be different if you include things other than just temperature. And that's what real global circulation models do. So the OECD just released a paper with a very sophisticated global circulation model and has a key section on what happens if we lose the AMOC. And that looked at a loss of the AMOC at between 2 and 3 degrees Celsius increase. And they said, what would happen is most of the Northern Hemisphere would experience a drying, except for North America, which would become wetter. India would lose half of its current rainfall. So we're talking serious changes to the capacity to have both industry and agriculture where we currently have them on the globe. And the conclusion was that it would be a catastrophic impact on food security. Now, they modeled it 2 ways. One, the AMOC in isolation, 2, the AMOC on top of 2.5 degrees of warming. And on the AMOC alone, what you found was the suitability of the Northern Hemisphere for humanity was substantially decreased. So there's regions, particularly Europe, where it's no longer suitable for human habitation, which is rather more sophisticated, significant than what Richard was saying a short while ago. If you have what we're likely to have, which is AMOC combined with temperature rise, then you actually have an increase in the suitability of the North America, but still that substantial fall in the suitability of Europe for human habitation. And the biggest changes were looking at what happened with actual farming crops. So this is now looking at the impact of the temperature on the right-hand side, temperature and AMOC changes. And you have an effective collapse of the capacity to produce wheat and maize in North America, Europe, China, South America, Southern America, and Australia. So this is the range of suitabilities they're looking at. And you've just focused on the regions where there's a 60% to 100% fall in the suitability of those regions for growing those crops. There goes the North American wheat belt. There goes most of Europe's capacity. China's is gone, Southern Africa is gone, and Australia as well, and even more so when you look at the case for maize, for corn. So they're talking about something of the order of an 80% fall in our capacity to produce crops. And when you look at in terms of the amount of land suitable for farming, you have a fall in the amount of the Earth's surface which is suitable for wheat from 20% to 8%, a fall in maize from 13 to 6%, and a small rise in the amount that's suitable for rice. In other words, we're going to have a collapse in food security if the AMOC gets turned off. And they said this would have a catastrophic impact, completely different to the statements that were used in Antop's paper and reproduced by Dietz. And they found the closest analogy to the climate for the Northern Hemisphere is going to be the Sahara. India would lose 70% of the summer precipitation. Most of Europe would be unsuitable for farming. We'd have a substantial reduction in global output and exacerbate global inequality. So no, Richard, shutting down the AMOC is not good. It is disastrous. It's only bad economic models that show this. And in fact, this paper critiques several of your papers. I say many of these have impact with changes, including the water cycle, which are left out by these small economic IAMs. And they said, some studies have argued that the collapse would have a net economic benefit. This seems untenable. So economists are making assumptions which scientists receive as untenable to reach their conclusion that global warming is no big deal. And what should have been the conclusion of Dietz was that if this is the result of intelligently integrating all the arguments economists have about tipping points, there's something wrong with what economists do. Instead, they perpetuated the use of quadratics despite the fact that they were modeling tipping points. They extended the trivialization of climate change in general to the treatment of tipping points themselves, and they provide a conclusion which will be cannon fodder for climate change deniers like Bjorn Lomborg. It won't be long before this paper turns up in his studies. And they're not based on economic analysis. This is what I find quite bizarre. These results are not based on taking what scientists have done in terms of empirical research about climate and then applying economic concepts to it. This is economists trying to do badly and succeeding in doing it badly what scientists do well, which is modeling climate change. So I think it's about time economists simply gave up on providing to make up their own numbers, accept what scientists said that 1.5 degrees would be catastrophic, work out how to finance a drastic reduction in fossil fuel usage, and work out how to transition to zero carbon energy systems, and fundamentally potentially prepare for war-style rationing, because the tipping points start causing serious catastrophes in the next 10 to 20 years. We have to be ready for it. But there's no way we are, and I actually said, I think economists have a large part of the blame for pulling the wool over our eyes about the dangers of climate change.
Thank you, Steve. Questions from Daniela? Thank you.
Thank you for a very interesting presentation, Steve. I have a question about the quality of papers. I don't know if you or other researchers have somehow tried to generalize basically the average amount of mistaken claims in papers on climate impact, for example. Because it's one thing when you're making, when you're publishing a paper that predicts a particular experimental outcome, then you can reproduce a paper and you can test the claims. It's completely different when you publish a paper with predictions about the future and there's no clear way of reproducing it or testing it. So what we end up with is that we rely on other researchers or experts or just lay readers who read the paper and potentially see the errors in reasoning. But those errors in reasoning are usually not severe enough for the paper to be retracted. So what we end up with is that a lot of the scientific literature contains mistaken claims, bad reasoning. And the question is, do we have any data, any description of how bad the situation is?
I must admit, I've been horrified as I read these papers by how bad the assumptions made by economists are about the impact of climate change. For example, in 1991, you have Nordhaus claiming that 87% of American industry will be unaffected by climate change because it takes place in carefully controlled environments. Now, to look at the list of industries he says are carefully controlled, it's all of manufacturing. He even included mining, thinking only about underground mining, all of services, wholesale and retail, all of government, all of finance, insurance, most of real estate, and most of transportation. It's that 87% will be unaffected, negligible damages, which is a classic case of mistaking climate for weather, and fundamentally saying you're only exposed to climate if you're exposed to weather. That's nonsense. But that is a common assumption in neoclassical climate change economics, and it's continued on to today. You also see them using current climate and GDP data to predict the impact of climate change. Now, the point I would make on that front is that it's pretty much saying it doesn't matter how you change the temperature. You can change it in any way you like, it'll have the same economic impact. If you think about what determines the temperature on the planet, it's three large categories: astronomical details, which means that given where the Earth is in the Goldilocks zone around our planet and its angle and inclination and so on, the average temperature of the planet is -18 degrees Celsius. Then you have the component contributed by global warming, which is all the greenhouse gases, including, of course, water vapor, but the fundamental swing variable is carbon dioxide, which makes that temperature about +13 degrees. Now, that's what's an issue about global warming. Then you have whereabouts are you on the globe and how far you are from the oceans. So how far are you from the equator, how close your city, et cetera, et cetera. Almost all the data that economists have used to fit the empirical models is the third category. So they derive parameters which tell you what's the impact of being a certain distance from the equator and a certain distance inland and so on. And they then apply those parameters to the impact of changing the amount of carbon dioxide in the atmosphere. It's ludicrous. And there's no way that I can give any justification whatsoever for those sorts of assumptions. But the result of it is that it ends up assuming climate change is a trivial issue. Now, if the assumptions are correct, they'll be right. There'll be nothing to worry about. We'll be laughing at ourselves in 20 or 30 years' time. If they're wrong, we'll be possibly dead in 20 or 30 years' time.
Thank you, Steve.
I don't call that a simplifying assumption, in other words. I call it a critical assumption. You have to test very carefully, and the scientists look at it. Believe me, they're not particularly respectful of what they see as economists have done.
So just, Chair, I'm going to take Chair's privilege and take the next question. If the, so essentially, what we have is a question about how data is treated underlying a larger moral economy question of, what is the question? Because there seems there's one side of things where there's the climate denial, and I don't think anybody here is in a climate denial situation. Most scholars are not in a climate denial place, climate change denial place. And then there's a whole set of debate about whether the data is helpful. And then there's what's going to happen, which is about things other than climate because or things other than temperature, because there is human response. It's like explaining the income substitution, effect to a toddler. Do you know what I mean? Kind of go, yeah, there's only this much chocolate, but there's this much broccoli. You know what I mean? So, it is how you kind of go to it. So my question to you is, because what in trying to overcome the very severe limitations that you have demonstrated there are for some of these modeling things, and some of them to do with the assumptions about what the effects mean for you, and coming out of what you've just been saying, is the question, if I asked Richard a question about what data should be looking for, is the question then about mitigation, or is the question about narrative?
About which again? About narrative?
Narrative, yeah, about whether the narrative is right or wrong, or about whether the action should be, what the
narrative is wrong. The narrative is wrong. The narrative is using fundamentally the geographic climate and income relationships as a predictor of what's going to happen as we drastically drive the temperature level of the planet outside anything humans have experienced in their roughly 1 million years on the planet. And the level of volatility that will generate in the climate is what's worrying scientists. They can see things like the storms which wiped out Vancouver's transportation nodes just a few weeks ago. This hurricane that's ripped through America a few days ago. They're saying that sort of climate volatility is going to become the norm. And the sedentary societies we've built in the last 10,000 years of quite dramatic stability compared to the previous 800,000 years were an essential part of being able to build an industrial civilization. And we will destroy that by putting the temperature up by increasing global warming. And the assurances economists give about it are based on completely the wrong sort of data. And even when they do now start taking the right sort of data, they're looking at change in GDP and temperature over time. And that's papers like Khan and Mahadi's, for example, which has just been published in Richard's journal. What they do, they literally linearly extrapolate the trends they found between 1960 and 2014. They linearly extrapolate those trends between 2020 and 2100. Now, that is again assuming there's going to be no tipping points. And then when you see a look at tipping points, they treat tipping points with quadratics. Now, I can easily fit their data with a logistic that matches what the quadratic shows for the small level, and then shows catastrophic breakdown a short time ahead. So I think we simply have to stop listening to the economists. They should not be attempting to ape the scientists. What they've done fundamentally is breach their own rules about specialization. They say you should specialize in what you're good at, comparative advantage, okay? What have they done? They've duplicated what the scientists do in terms of global circulation models, and they've done toy trivial ones about that, rather than saying, okay, here's what the scientists think, then what are the economic impacts of that, and how do we resource fighting it? So I think economists have been an enormous disservice to humanity, and there's no way they're going to reform themselves.
I love econobashing more than most, I have to say. So, but what I would like to do is take particularly the point about volatility and how it is integrated into narratives and models, and sort of bank that for something we can talk about later. Dan has a question.
Yeah, I'm not sure whether this is something that should come up in the panel, because I think Richard has probably something to say about this as well as Steve.
Yeah,
and
I would imagine.
I'm not asking this because I know the answer and I'm kind of waiting to pounce, but simply I don't know the answer. So the question is really this, and Judy can decide whether it goes better elsewhere. The IPCC, the International Panel on Climate Change, we all know about. You know, it's a scientifically driven organization, but they got economists there.
Yep.
And they work amiably together. And so I'm also not opposed to the econobashing or even the scientist bashing when it's deserved. But your statements about, you know, the polarization, how do your statements about the polarization get rationalized when you have a really top-notch scientific organization working with economists? And I mean, you know, I know people on IPCC, they know Nordhaus, they know what he did. So how do you rationalize that? What do you think about what goes on there, maybe, and what is the process, right or wrong?
It's fundamentally the same thing that happens in universities, and that's academic silos. So and this is it's a piece of respect by professionals of one discipline to another to say, I'm not going to dive into your discipline and criticize what you do, because there may be something that you know about your discipline that I don't know, that means I'm going to make a fool of myself. So chemists are unlikely to dive in there and criticize physicists and vice versa. And that's justified because they are genuine sciences. The same respect is given to economics, and it does not deserve it. Frankly, doesn't deserve it by a huge margin. There is so much unacknowledged ideology built into economics itself. It's a riven discipline. You know, I'm from an opposing side of economics to Richard, for example. And there's a majority which is almost impervious to criticism. Now, what that meant in terms of how the IPCC is put together is the economics chapter 10 of volume 2 of the IPCC 2014 report, was one of the two main authors was Richard. I've forgotten the other one. And they came up with saying medium evidence, high agreement that climate change is trivial, fundamentally. That's one of their frequently asked questions. And one of the FAQs also includes, are other industry sectors affected by climate change? They gave the same answer as Nordhaus in 1991, that if you're not exposed to the weather, you're not exposed to climate change. So the siloization means that scientists don't go and check those chapters. But what happens with politics, of course, and I'm speaking with quite a few politicians, they send their advisors off to go and read the document. All they're really interested in is a section about the economic impact. what they read as the economic section of it is ignored. And therefore we end up with politicians responding to what the economists think is insignificant, and hence we get useless international meetings where nothing is ever agreed, and the seriousness of this is not really understood by anybody. So economists have been blocking scientists, warning about this really for 50 years.
I think we should put the word some in front. I mean, as a person with, who's an economist, I completely agree with particular aspects and groups, of what you're saying. But there is within the discipline as a whole, as an economist and a historian, there is among scholarship as a whole, like there's some areas of science that have, done, kind of harm to, and some areas of data science that, haven't been exactly, kind of whiter than white. So the very fact that this chat is happening demonstrates that there is the possibility not for this hegemonic, view of economic modeling to, give these wild, not wild, but far too moderate predictions based on, some Gaussian misconception. So I'm hoping that we can sort of talk a little bit more about whether both the questions and the data and then the methods for putting them together, can be fused in a slightly better way. Daniela, do you have another question for Steve before we move on to you?
I have a lot of questions actually. One question that is related to what we just touched on is what about the lobbyists? Any ideas, any data, and at what the impact of political lobby, diplomatic lobbying can be on papers and claims?
Good question.
Yeah, I think it's indirect. Certainly lobbyists affect what politicians do. But in terms of the lobbyists affecting what economists write, economists actually believe this stuff. What then happens is the lobby groups will pick out economists that believe this stuff and then fund them, whereas people who oppose it don't get funding. So you get a trivial amount of funding for people who are critics of neoclassical economics, especially on climate change. You get a large amount of money, even though they complain themselves about not having enough money, a large amount of money what the neoclassicals do. So the effect of the situation is that the fossil fuel groups end up enabling the economists who are not climate change deniers duty, but they're climate change trivializers. And that's what they've done. And as I said, I'm giving a talk soon, one of my lines in that is that the fossil fuel industries have fought the war against action on climate change, but economists have made the bullets.
There is the question. So if we clarify what you see as the problem as trivialization, then the question further arises, is it trivialization of the ecological phenomena, or is it trivialization of the effects on human activity?
It's both.
Okay.
I mean, they treat the environment as something you go along and tickle a panda, not something which if it doesn't exist, you die. And that's why the whole idea of willingness to pay, even though they didn't actually use willingness to pay, they simply made up two numbers. When you talk about willingness to pay, that's the sort of thing where you value a nature reserve versus turning the nature reserve into a skateboard park on people's willingness to maintain the nature reserve. Now, you don't die if you shut the nature reserve down. So it actually makes a certain amount of sense with small scale studies like that. But to apply to the actual environment, say, well, what are you willing to pay to avoid a 2.5 degree increase in global temperatures? Nobody, people, they didn't even know whether they should wear masks in crowded spaces, for God's sake. It's not the sort of question you can answer. And your whole tendency, they're using entirely inappropriate methodologies. Really, what I see it as a case of boys with toys. They've got a bunch of econometric techniques. They love using them. Here's a way of writing a few papers and getting them published. And that's really the seriousness with which they've treated climate change.
So the question for me then is, how can we modify the question so that their tools or toys could be actually utilized usefully? Is that a possibility?
We have to insist that no economics paper gets published without being refereed by scientists as well.
By scientists as well.
On climate change, okay? No paper published by an economist without being refereed by at least two scientists.
Okay. Daniela, do you want to ask another question, or do you want to move on to your paper and then we can take this up in a...
We can move on, I think.
You want to move now? Okay, I'm going to give your bio and your intro. Thank you. And thank you, Steve. I'm looking forward to returning to this in terms of like the kind of effects and trivial and question thing later. So thank you very much, Danila Medvedev, Dr. Danila Medvedev, who is an applied futurologist and architect of Neurocode software for collective intelligence enhancement and complex modeling. Danila frequently speaks to corporations about innovations, technological progress, and processes, I imagine, and the future. And what your presentation today is going to do is look at modeling long-term structural technological changes and their impact. I hand over to you if you can screen share. Thank you. You're on mute, Danila.
Okay.
Thank you.
You can see the screen shared.
It's not showing up yet. It says, yay, got there. It's there. Thank you.
Okay. So thank you very much, Julie, and thanks to the previous speakers. What I see is problem is that a complex situation is being decomposed by the researchers, including the economists. And instead of dealing with the entire system, what we have is basically poor models for dealing with parts of the system. So we lose all the interactions. And in addition to that, we can have egregious mistakes such as those that were mentioned. So my point and suggestion I'm making is that the approach to understanding long-term changes in the economy should be based around structural modeling, including at least three subsystems: the environment and the climate, the economy, and the technological landscape, or the set of technologies. And I do have some experience talking to corporate people and government people about what kind of strategies they have, what kind of long-term view they have. And to me, it's clear that there is a very big limitation in how these people can potentially understand and describe the future. And it follows that if they cannot describe the future, be it the future of technologies or the future of climate system, then it will not be possible to reflect that anyhow, because they will only understand simple extrapolations as a view of the future. So what we have to do is we have to go beyond human, intuitive human understanding, and instead use modeling where the results, well, I mean, they will not be objective, of course, but at least they will be will not be limited by our ability to just process the system in our head. As has been mentioned, the existing models of climate and economic relations are not adequate. One of the clear examples is the dynamic integrated climate economy model by Nordhaus, which was revived a number of times, and there has been extensive criticism, and it was extended, for example, with the pliable abatement cost elements base model, which includes technological change. And also it argues that it's not possible to have one path and argue that every country and the planet and the global economy will follow this single path, but instead we have to allow for multiple paths between which we will, or corporations or the governments will change. So that means we have to somehow model a scenario network, which I would say completely breaks the extrapolation methodology and also most of the simple mathematical models, equilibrium models that economists often use. So that means we have to switch to different research tools, including models and simulations, if we are to have any chance of representing the situation accurately. A complication here is that climate and the economy are what Timothy Morton calls hyperobjects. They are extremely complex objects which cannot be grasped by an individual human, by an individual researcher. And that is related, of course, to silos and specialization in science as well, because no one can understand all the aspects of biology, agriculture, economy, finance, climate, science, etc., etc. So what we can do is we can apply our cognitive resources, our mental facilities locally when understanding some part of the system. But then it follows that a collective cognition is required. Just as an ant can only apply local cognition when choosing whether to go left or right, but the overall processes that happen in the ant colony, they are collective and distributed. So that means when we're thinking about the methodology and epistemology of understanding climate change and climate change impacts on the economy, we have to think about a collective cognition process by the scientists. So it's no longer enough to just think about how one particular researcher or a general reader will understand something. We have to think about how knowledge is collected from different sources, how it's accumulated, and how we can build a big picture from small parts that we only can understand. And my suggestion is that what we need is we need a complex model for the economy and also for the relation between the climate and the economy, which will be somewhat similar to the complex models which were created for the climate itself. Turns out that many climate scientists have created open source and closed source scientific simulations, which quite accurately describe what happens in the climate by basically breaking the planetary surface or the volume of the atmosphere into many blocks and then running simulations of where the wind, the water vapor goes, how energy is transferred around in the system. And what might be done is we might have an overlay or a similar parallel model of the economy with the same accuracy and the same complexity. And I will say a few words about the methods for that, the tools and the resultant applications. So speaking of methods, it's quite simple. There are equilibrium models which are not sufficient for dealing with this complex problem. So we have to use methods from modeling, such as system dynamics, discrete event, and agent-based methods. And we have to use the overall system approach. So I would say that no economic paper should be accepted unless it clearly explains how the economist or the researcher sees the system that he describes and tries to explain, like what parts have been selected as important. And all these assumptions have to be formally described and marked down, because otherwise it's impossible to reproduce the thinking. So what we have to deal here is not reproducing a physical experiment. We have to think about reproducibility of thinking. So when we have a complex system and a model, a mental model of that, different researchers, different thinkers should come to similar conclusions if they follow from the same premises and follow the same thinking process. So this requires very clear descriptions of what the assumptions are, what the parts are, etc. And a consequence of that, and the consequence of the complexity of the climate and economy is that we have to implement a multi-scale simulation and a multi-scale research approach, because the system is so complex. It's not just large. It not only has many elements, but it also has many subsystems which include other subsystems. And the system has very complex feedback loops with many steps, not just one or two, but sometimes as many as 10, for example. And that means if we are to understand it all, we have to have a complex simulation. And in order to understand this complex model and the complex simulation, we need basically tools and interfaces for dealing with this multi-scale model. So that means that we need somehow to be able to zoom into the details of individual assumptions. Like, for example, when we get some data about the value of the environment, and we have an assumption that it's okay to ask people how much they're going to pay. So that is a minor aspect of this particular subsystem, but it might be important. So we should be able to zoom from the big picture into these small details. And that has to happen not in individual papers, but it has to be kept in an overall description of the system. So that requires a different approach than just publishing papers. In addition to that, in addition to these methods that I mentioned, we have to understand that we're dealing with the future, and that means there is a separate part which is related to forecasting, futurology, and strategic planning, which should also be modeled and described somehow, because the decisions that the decision makers make and that the public makes, they are dependent on the processes which are used in futurology. So when the government decides what it's going to do about climate, what's important is to understand what's the decision-making process inside the parliament, for example, or how the lobbying groups operate in this particular country, because that affects the outcome. So if we want to have an accurate prediction, we have to somehow model this social subsystem and social political subsystem, not just the economy, not just the environment and the climate. Here is a very rough take on how we can combine these long-term changes into a model based on these three strategies. So the foundation can be seen as a scenario network map, a method which was developed by Dennis List, an Australian futurologist. So it's basically not just one scenario, it's a graph placed on a timeline which describes an arbitrary number of events connected by different influences, including causal links. So that is a foundation for describing the long-term view, like what will happen as a result of what are the prerequisites for particular events. And then when we look at this scenario network map, when we model it, basically a number of tokens move on the map and events are triggered, and then different parts of the simulation can be activated, including agent-based, etc. And this scenario network map can be predefined. It can be created by experts in advance, or somehow it can be modified at runtime. But what's important is that it's shared, because as I said, the system is complex. It's a hyperobject, And the processes that needs to be taken into account, they number much more than just 10 or 20. If we go back to the tipping points illustration that was shown by the previous speaker, there are, I think, about 15 or 10 to 15 events there. So some ice going up in the West Arctic, in the East Antarctic, in the East Antarctic, in the Arctic Sea, and that is not sufficient because the number of events which are connected through this feedback loops is much more. It's hundreds or even thousands. So that means this map should be shared, and it should be seen as basically information artifact valuable by itself. Just like, for example, we today we not only have papers, we also have data sets. In addition to papers and data sets, we will likely need something like this scenario network map, which is shared between different researchers and opinion leaders and experts. And when we talk about something, we should refer to this. It's sometimes called a boundary artifact or something like this, boundary object, something which is used for experts from different fields to converse about something. So that's the foundation. And then the agent-based and that aspect is relatively straightforward. So we can model regions, companies, and allow them to make certain decisions in the simulation and then run Monte Carlo or something similar. What's important is that we also model technologies, and here there is a serious shortcoming, and it's not limited to just the works of Nordhaus, but pretty much no one in the economics describes or understands the substance of technologies well. And if you go to the IPCC documents, they basically don't mention this at all, or just barely mention. They say there is an assumption that there will be some future technologies which will help like mitigate something. And then there are no details, no references, no links to any additional considerations. There is one researcher, at least Jeffrey Funk, who wrote extensively about the structure of technologies, where basic technology enables more complex technology, and where you can have quantitative modeling and model with quantitative relations. Like you have a lighter material, which means that a bigger technology is less, for example, more effective, less energy hungry, faster, and so on. So when we think about the technological change related to climate, including energy transition and decarbonization, we need to model the structure of technologies as well. And then it's of course related to the need to model investment in technological development, and compare it with investment in mitigation and so on. So that's something which is not done, is barely done at all, and it needs to be included in the model. And then the summary of that would be system dynamics, which can model the resources, available resources, like the natural resources, for example, and some parts of the climate model. So in terms of actually doing this, on the one hand, we've had tools such as general purpose simulation software, GPSS, for 50 years. And on the one hand, it's just doable. You can just go and simulate something. But then when you look at the actual practice and the actual cases of GPSS and more recent software such as AnyLogic, the existing simulations are never complex. So we don't have any economic simulations which are comparable to the climate simulation. And usually they concern just a few subsystems of the company, even when it's related to strategic management. So what I think is important here is that to create these complex models, we need not only simulation software which is capable of running these complex models, but we need to have distributed collaborative editing software for actually describing these models and working on them together. So that's what I have been working on with NeuroCode, which has a new zoomable graphical user interface that allows exploring a scalable big model with formal parameters and visualization. So I think that if we look at what is possible with modern computers, such as the recent demo of Unreal Engine 5 and Matrix collaboration, where a huge space, a huge city is simulated very accurately in terms of visual representation, we have to ask ourselves, why can't we simulate and model complex economies and societies and the future progress? So I think that has to be done. And if we do that, if we put this into practice for corporations and governments and make it possible to plan for 2050 using this approach, then we can finally have the answers and can make the right decisions. And what is interesting is that next year there will be a 50-year anniversary of the limits to growth. So to me, it's interesting what kind of benchmark, what kind of projects in terms of simulating the world will we have next year to basically answer the same question, like what will happen with the global economy and the planet. And I hope that the World 4 can be done next year and can give us some of the needed answers. So thank you.
Thank you very much indeed, Danila. So a technical solution-driven approach. Actually, I'm going to invite Dan, because Dan is the technical. Go on. You've already put your hand up, so that was, I was going to invite you to ask questions first. Is that okay?
So, you know, this is very interesting to me. I actually feel a little bit awkward, you know, if I weren't giving a talk here and this material were not so close to the bone, I would just ask a question. But I feel like I'm self-promoting by asking a question, which isn't good. But I'm gonna first try to answer your question about why you can't use modeling to figure out the dynamics. That's really what your question is. And the answer is, you never can figure out the dynamics by looking at the modeling. You have to guess the dynamics and then use the modeling to test a hypothesis formed on the basis of that guess, that theory. It's deduction. And what you're saying, what you're asking, what lots of people ask is, can't we use data science inductively to guess the answer? And no, is you can't. And
I would expect that answer
some
from a
isolated examples, but generally speaking, no. So you have to guess. You have to. That's where you have to. Well, you know, it's just got to come from you.
Okay. So
what is it? What is it?
This is why the narrative and the thing matter. Specifically on what Danila has presented as the data science approach that he's looking at. Have you specific questions about how the you know, the different elements of it are interacting, or would you rather discuss the, you know, why data science seems like an approach? One thing I will be asking you in the roundtable is why you think the traditional model from the natural sciences, which you are trained in, you know, has not infiltrated as a discipline within data science. Because, you know, that's got implications. But is there something specific about Danila's, you know, models here that you would like to ask?
Well, I had questions about three things. I made some notes. First of all, I'd like to know more about what you mean by the term path dependence. I'd like to know sort of where you divide your understanding of the word modeling from theory. And also, I'd like to know why you have conviction that it's complex systems that are required, or complex systems theory, which is needed to describe the world. What is the evidence that the world that you're seeing is complex?
Okay.
Do you want to answer that now? Thanks, Dan.
So path dependence is basically we need to take into account when particular mitigation or technology development steps will occur. And it turns out that, I mean, even if we just look at the most well-known graphs of CO2 concentration going up and the temperatures going up, and then we ask how can we decarbonize, and then so there's a graph going up and then it goes down, and the longer we ignore the problem, the sharper the fall that is required. So the politicians, they can still make the case that, yes, if we really try, like in 2 years, we will be able to decrease CO2 emissions like in 5 years. But if we wait 7 years, they will have to do it in 0 years. So it turns out that we need to take this into account because it's obviously easier to do something small scale than to radically change the entire economy in just 1 year or instantly. So path dependence is that when you're trying to model what happens in the economy, you have to consider different sequences, different of steps.
So can I'd like to interrupt just to sort of restate what you said to make sure I understand it. Where nonlinearities, or what Steve might call tipping points, are very important, then they must be avoided. And so the path that you take to avoiding them is significant. So if you start today to avoid the thing, then that's different from starting the day before and when you're forced to do something radical. So that's what I think that's what you're saying. When you get near a cliff, you got to avoid it, and the path you take or the time you start makes a big difference. So assuming that's what you said, what if there are no tipping points? What if it's totally linear? Does it matter when you start?
Well, if everything was totally linear, then there wouldn't be much path dependence. But what I think is that, well, the world is clearly sufficiently complex that there are at least some tipping points. Like, for example, when the public opinion changes in a particular country, and at some point a vote is undertaken in a parliament, and the parliament decides on passing a law. So that is also a tipping point. There are not just those 15 tipping points which are described in the climate literature, but they're literally all around us. So we have to consider them as well. And also, when we ask questions such as, can we prevent the catastrophic consequences of climate change by limiting like CO2 or temperature to a certain amount? Sometimes we may need to ask more specific and narrower questions, like can we avoid a catastrophic consequence of, for example, ocean acidification, or of Gulf Stream shutting down, or of climate-related war in Syria. So those are all related to paths, to different scenarios, and so path dependence is important for being able to answer these questions.
Dan, do you want to respond to that, or do you want to talk more after you've given your paper? We'll see if there's any questions from Steve or Richard on what Daniela was saying.
Okay. Then the second question was about the distinction between a model and a theory. And I'm using these words, the word model, very well, generally and flexibly. So there is a clear definition of what a simulation is, but when I'm talking about modeling, I refer partly to the need to describe a system. So that's the most basic level of modeling. And then simulating certain interactions within that system. So that's the second part of the modeling. And also what is, I think, important is that when we're dealing with something as complex as climate plus economy plus technology, we can't make the accurate model on the first try. So we have to plan for iterations, and we have to understand that for a few years, the models that we would make would be incorrect, but hopefully they will be increasingly more and more accurate. And those great errors which were described by the previous speakers should eventually be eliminated. And we should get to shared models. And this is also related to the concept of shared mental models. Basically, when we are thinking about the system, it helps if everyone understands what the components of the system are the same, because then it's easier to like discuss specific predictions and predictions about specific parts. So that's what I think is important. And the theory, we are so far away from having a theory of the future, the theory of history, the theory of the economy. We can probably claim that we have a theory of climate, but it's still incomplete very much. So to me, it's less about the theoretical work, but more about the modeling and basically structured communications between experts around these models.
Thank you, Daniela. We will return to models, hypotheses, and theories later, I hope. Richard, Steve, both of you look like you wanted to make some.
Oh, sorry, I missed Daniela's talk, so I have no response to it.
Okay, well, thank you for what we'll actually, I have the slides. Why don't I put them in email for you so that you can see them for later? Steve, you unmuted there. Do you want to say anything?
No, I was basically saying I don't need to ask a question. I'll wait till after the general panel discussion.
Thank you. Okay. Okay, so Dan, we shall move on to your presentation, if that's good with you. So Dan Seligson lives in Palo Alto. He received his PhD in low temperature experimental physics from Berkeley in 1983. He has lived and worked in Silicon Valley ever since, first as a technologist, a manager, an entrepreneur, and an investor. And since 2015, as an author interested in the role of family in macroeconomic outcomes. And the abstract for your paper now is the economy is a dynamical system set in the natural world. From its behavior over time, we extract an estimate of the cost of climate change. Dan, are you able to share a screen?
I'm gonna try. Let's see what I got here. And
Sounds good.
Put this
Yep.
on here.
Keep it brilliant.
Okay.
You're on.
Are we on? Okay, great. So this is describing some work I've been doing with MIT historian Anne McCants for several years. I've discussed bits of it with all but one of you in the past. And it's a bit contrarian, but it works for me. Okay, so I want to talk about estimating the cost of global warming. So let me get rid of this thing here, which is in the way. Okay, sorry. Right, so economists talk about production functions, let's say y is a function of P and C, where P is some atmospheric and geophysics and C is the climate. All right. So that kind of thing is done all the time. What do we do now? Oh, here, excuse me. Okay. What we want is the derivative of the production function with respect to temperature, but that's because because both P and C are temperature dependent. This is the sum of two terms. One is the sensitivity of the production function to the physics in constant climate, and times the sensitivity of the physics to temperature. And the other one is the sensitivity of the production function to climate at constant physics times the sensitivity of the climate to temperature. All right, so you could write that exactly this way. You got the total is the sum of these two terms. Nothing controversial there. I want to say about this term, though, that I'm just going to say for purposes of this argument that climate is temperature, so we're really looking at the derivative of the production function with respect to temperature. And I agree this is a simplification, but it's one that I think underestimates rather than overestimates the effects. Okay, so let's just remind ourselves about a little bit of algebra. If we were to divide everything by y, that makes the derivatives scale free. And so that gives us terms like 1 over y dy dx, but that's just the derivative of the log of y. So we look at our old equation, it says the derivative with respect to temperature, the log of y is the sum of a physics term, that is understanding how the physics changes with temperature, and the other is just the economic history term, and that is how the production function changes with the temperature at constant physics. And what I mean by constant physics? Well, I mean that the oceans are where they are with respect to the land, and the weather is what it is. That's really what I mean. Okay, so Nordhaus says that the second term, the temperature derivative of the log of the production function, is 0. Right? We all know that. We know he said it. Other people have said it. In fact, a lot of other people have said it. Doug North, the institutional economist of some note, has said it. Hall and Jones echoed the same thing. Acemoglu, Johnson, and Robinson, make the big deal about this. They say it over and over and over again. Danny Roderick, president of the International Economics Association, or at least was until recently, and Subramanian Trevick, they say the same thing, that it's all about institutions, temperature has nothing to do with it. And lots of people at the National Bureau of Economic Research read these papers, approved these papers, and let these papers get through to the Quarterly Journal of Economics, to the American Economics Review, and then they were all approved by the Nobel committees and the Clark committees, et cetera, et cetera, et cetera, et cetera. So everyone believes this. But we have a problem. And the problem is that the economy is a dynamical system, and no conclusion drawn from the observation of a dynamical system at a single point in time, has any more validity than the following statement. The number of lines you can draw through a point is 1. Obviously, you can draw more than 1. You can draw an infinite number. So you can conclude nothing from what Nordhaus did. You can conclude nothing unless you really understand. Actually, you don't even have to understand it. You just have to interrogate the temporal behavior before you can make some sort of bold statement about the dependence of that dynamical system on pretty much anything. So this whole problem is addressed in a recent, well, it's not that recent, 5 or 6 year old paper by Paul Romer, which I am not going to dwell on here, but I highly recommend it. And he said, basically, he said, the economists have lost the thread of Solow and others in growth theory. Okay, so now let us ask, how might temperature, so if we can't believe Nordhaus that says, you know, on the temperature dependence of the production function, who says it's zero, let's just start at the beginning. How might temperature bear on economics? So I want to start by reminding us that economics is a study of human behavior and scarcity. Many people will say, well, it's the study of the allocation of scarce resources, but allocation is a human behavior. So I'm just going to say it this way. So it could affect it through agricultural productivity. Okay, there might be some sort of peaked function, maybe broad, maybe narrow, that says that agricultural productivity is peaked at some temperature in particular. And human productivity, there's, you know, how long can we work? How fast can we work? How hard can we work as a function of temperature? And there is some evidence that gets worse at higher temperature because you can't cool your body fast enough to keep up with it. And then there's the next thing, and that is the thermodynamic issues. Well, it costs to heat things, and it costs more to cool things. So that's the second law kind of argument, which should say that things are worse at higher temperature, assuming that you have the technology to heat and to cool, and you have the energy to pay for it. Okay. And the second thermodynamic argument is that things fall apart faster as T increases. This is, you know, comes from Arrhenius. In the case of organic matter, the ratio of decay rates is 2 when the temperature difference is 10 C, or people often write this as Q10 equals 2. But if Q10 equals Q, then Q1 is 1.072, implying that food, clothing, shelter, and other natural products fall apart 7.2% faster for every added degree of temperature. These are empirical facts about the world. So how much might temperature bear on economics? That was how does, you know, what are some ways, but actually how much? So I'm going to first remind us that the performance of a simple dynamic system with moving parts, for instance, a pendulum or a motor, is determined by its sources and its leaks. So, you know, on this planet, delta T is 40, Richard said 50, whatever. So Q40 is 16, Q50 is 32. That would, if the performance is determined by its leaks, that would say that over the temperature range, there is either a 16 or a 32 times difference in performance expectation. Since GDP varies by 100 or 200 or 300, depending on who's doing it, you know, this is going to be a contributor, certainly not the whole thing by any means, but it's probably part of it. Okay. An economy whose leak rate is temperature dependent is not likely to behave worse than Q1. So, you know, I want to go back to this Arrhenius thing. We are all aware of the fact that during the summer, you know, the pears in our fruit bowls decay faster, attract fruit flies faster than they do in the winter. We have refrigeration for all these regions. So this natural rate of biodecay is among the most evident of all temperature dependent phenomena in the world. So if it's the most obvious, it's probably the biggest. So an economy, so I'm going to say that if the leak rate is temperature dependent, it's not likely to be worse than this. Okay. So if I put it into the original language, trying to look at the temperature dependence of Y, well, on the one hand, we have it's 0, that's the Nordhaus term, but it's probably an underestimate. So it's this thing in the middle, and it's probably less than Q1, which if I stated in logs is not 7.2, but 0.069, okay? So that's the case. So if you just take the average of those two things, you get, you can expect that the log of the temperature dependence, the temperature dependence of the log is minus 0.35 per degree C. All right, that's just estimating, that's just averaging the extremes we're likely to encounter. So now I just want to remind us again of something else. if Y is per capita GDP or GNI, then the Human Development Index is a lot like log Y. So I've just plotted those two things out. The correlation is 0.94, very high. A lot of the loss of that correlation, or that 6% loss, comes from oil-rich states who have a lot of money, but the quality of life is disproportionately low. So those are the ones in red. And in the lower right, all I've done is showing you that log GNI and log GDP are the same thing. The correlation there is like, 0.995. They're the same thing. So now I move on. What about the history? I said we have to, if you're going to actually look at this, you have to look at the history. And by the history, I don't mean a story about climate changing in some such place. I mean the trajectory. That's what I mean about economic history. What is the trajectory of history? So this is the trajectory of 164 national economies from 1870 to 215 in HDI. This time series comes from Leandro at Madrid, and there's a bunch of stuff. And it's difficult to disentangle just by looking at all these things. But if you look, on the other hand, at the growth of the annual means, that's exponential with very small error bars. So period. It's remarkable. The time scale for that, the exponential time scale there is 68 years, in the log of the production function. There it is, Now, most of the trajectories actually follow the mean. So these things, most of the trajectories follow the mean, period. So what is the mean? Well, the mean is driven by an ever increasing body of collective knowledge, technical and social. So let's take the growth out of the data, So I'm going to go back. Most trajectories follow the mean. So if I take the mean out, we can see something. We can see something pure without this ever increasing body of collective knowledge, which is varying over time. And what do we see? We see that those same lines, which were following the mean, they're just constants now. We see over 150 years, because that's all I got the data. Richard mentioned that before. 150 years, that's where we have pretty decent data. There's the national economies maintain with respect to each other relative constancy over more than a century. It's not perfect. We can, if you want, I can tell you about all the imperfections in the data, but it's pretty good. And I can measure correlation functions and the rate of decay of the decorrelation. And if somebody here wants to know, I'll just tell you, you can correlate the front to the end, and you can look at the exponential decay of the decorrelation. And the exponential decay of that decorrelation is 626 years. And if you fix the data to account for the fact that he runs out of resolution, it's probably better, but I don't want to fix the data. So because of all this, the rich stay rich. I mean, what are we saying? Well, the rich stay rich. This is what Douglas North meant when he said that the second most important problem in economic history is to understand the persistence of the distribution of the wealth of nations, the persistence of the gross disparities in the wealth of nations. The rich stay rich and the poor stay poor. It's right here, And there are exceptions. These are 9 or 8, I don't remember. So we have Russia, big leap from Tsarism to the late 60s, then in decline. We have the GCC states, the Arabian Peninsula, where they're going down, they're basically flat at the bottom, and then oil. So oil brings them up. So, you introduce something really new like oil, free energy, work. Oil is work. So that changes things. And then we've seen some remarkable stories from the Asian tigers, all of those together. And we've seen Japan slightly different, Finland slightly different, but these, of all of the exceptions, these are the bigger ones, these are the biggest, and there aren't that many. But approximate constancy dominates. Like I said, the time scale for the decorrelation of this constancy is over 600 years. Okay, extracted from this 150-year data series. Okay, so how do we explain this? Well, the relative constancy of individual trajectories is easy. Okay, if you want to know, because if you want to ask what kind of dynamical system produces a relative constancy of individual trajectories, well, that if the economy is a driven linear dissipative system whose time scale is set by the useful lifetime of roads, which is maybe a decade or two, okay, then you get constancy. You don't need complex systems to explain this, okay? And Anne and I described this in our JOIE paper earlier this year, and we explained it some more in our social science history paper this year, and there's a new manuscript forthcoming, which goes well beyond what we did. And it has one dynamical system framework to get both the constancy and the global growth. All right, so, but what about the distribution? That only explains why things are constant. It doesn't explain why they're distributed where they are. Okay, so in order to explain, as I said before, it's a driven linear system. So the driving sources must be constant over 150 years, because if they weren't constant over 150 years, we wouldn't see constancy. And that rules out the new institutional economics' beloved institutions, because the institutions they talk about change on a time scale of a decade, couple decades. So that's wrong, period. And they must be, a reminder, so they must be economic. They must bear on scarcity and behavior. Otherwise, they can't affect anything, right? They're, I mean, it's not museums that are doing this, all right? And it's not the clothes people wear. It's not that aspect of culture. Okay, and the list of candidates that qualify is short. And it consists of three things. Maybe some of you know more, but I don't. Something to do with climate. We know that bears on it. Something to do with geography. That's why, you know, geography is really important, whether you're close to the water or not, whether you're in the mountains, all those things make a difference. And social norms, that is behaviors. Behaviors, that's what social norms are. That's the aspect of culture that makes a difference. Behaviors, social norms. Okay, so you put all this in, and then, you know, Danila has listened to me for hours and hours, and he knows where I'm inclined to go. And he said, don't go there. Just talk about climate. I said, okay, so we're just going to, so after you take care of the geography and the norms, what's left? And I don't mean what's left in the sense of we do one first and we do the, and then we do the other. We do them all at once. You have to do them all at once, because otherwise you don't have self-consistency. So it's that you find that the temperature dependence of the log of the production function is minus 0.042 plus or minus 0.008. That's probably about 2 sigma. That is it's a 2 sigma variance there. So this is at least a 5 sigma and maybe a 10 sigma number per degree C. So that's not 0. Okay, this has no overlap with 0. That's the Nordhaus estimate. It has no overlap with Arrhenius. Okay. But it's pretty close to what we guessed just by averaging those two. And I'll mention partly for Brad, who's not here, who co-taught a course with Melissa Dell within the past year or so. Melissa Dell, Jones, and Olkin estimated that the number was this, which is bigger than the natural rate. Okay, she doesn't offer any mechanism. So what do I observe about this? Well, our know-how, our collective knowledge all kinds of things about our collective knowledge, enables us to offset about 40% of the natural rate of biodegradative decay. That's what we know. So what can economic history tell us about the cost of climate change, which was the title here? So, well, it says 1 degree C of warming will occasion a 4.1% decline in global GDP per capita. That's what economic history tells us. And the consequences of atmospheric and oceanic circulation, inundation, conflagration, migration, acidification, etc., whatever they may be, I make no claims about them. Large, small, costly, beneficial, I have no idea, but they're additive to this, to first order. So this is a chart that Steve Keen produced in a paper a few years ago. He showed me in a conversation we had long ago. And this is, you know, remember, everything that the economists do assumes dy dt or d is 0. So this is just the physics term. So this is just what the cost of climate change is, assuming that temperature doesn't matter at all to the production function under constant physics, geophysics, whatever you want to call it. So I'm just going to look at that again. Okay, that's right there. I probably should have eliminated the last slide. And I'll put that side by side with the economic history term. So the economic history term, so it's within that band, okay, plus or minus 0.42, 0.042 plus or minus 0.08. That's what that is, all right? But remember, we have to add them. So when we add them, we get this. So all of those numbers are pulled down by this amount because that's what it actually costs. All right. And that's it. Thank you. That's the answer. That's the answer.
Because, you know, that's always a great approach in science. Okay. Thank you very much, Dan. Have I got questions from any of our panelists or comments on this? Who would like to? Daniela, Richard, have you unmuted ahead of, or okay, Daniela, here you go first. Thank you.
If Dan, if you can repeat basically the last part of your presentation where you were saying about okay, this is when you add it.
Right.
Can you clarify a little bit the logic behind this?
Yeah. So if you can see my screen. So remember, the total change of production function with respect to temperature, and the total change is the sum of two terms, the physics term and the economic history term. The physics term is remember, Nordhaus says this is 0. And so this is what everyone's calculating, all right? And what I'm showing is this term is not 0. So if this is what they've got, then you have to add it to this. So that's what I've done here. We've got these two things side by side. This is the physics term that everyone's calculating. This is the dy dt all by itself. You have to add them. When you add them, this is what happens.
Daniela, have you got? Do you want to see that bigger? Can you put that on?
I can see, but can you comment on the implications, like the logic?
Yeah, the number's a lot bigger than anyone's talking about. I'm not going to say, I don't want to present myself here as some hysteric. Not that anyone here is a hysteric, but I don't want to. All I'm saying is, this is just the cost. In other words, if I think there are two very, very different issues, and that really must be confronted. And one is there a tipping point? Is there a cliff? Because if there's a cliff, then really no one knows what happens on the other side of that cliff. And we have to worry about it. And, you know, Steve, in one conversation with me told me that he thinks the cliff is at 2 degrees. I don't know where the cliff is. Maybe it's at 3. I don't know. I don't know. But if you just want to calculate the cost, there are 2 pieces. And I'm saying one piece is wrongly calculated. And I'm telling you what it is. And whether the other one is right or wrong, I have no idea. I've spent no time on it, devoted no energy to it. I don't know anything about general circulation models or any of those things. And I'm not even going to speculate on them. But let's just say that this is this physics thing that Steve Keen has produced, a summary of results. Okay, and so those are some numbers. We have to add them to that. And when you add the 2 together, these are not log things. You got to convert them to logs and add them and then transform it back. And you get this. And here, instead of having, here my red line is just in the center of the other one. And I've used error bars to, at the width of the range of my data, to say, okay, this is what the physics term plus the economic history term is telling you. It's bigger than you thought. Whether that's something we can stomach or not, I don't know. If we don't know what the hell happens after 2 degrees with the shutdown of all these things, and I'm not going to comment on it. All I'm saying is that half of the thing, there are 2 terms. There are 2 terms, at least, and there are at least 2 terms. And if you look at these 2, and the economists up and down the entire hierarchy say it's 0. And I'm telling you, it's not 0. They made a mistake. They're wrong. Okay. And any physicist, any mathematician who looks at what they do would say, that's wrong. Period.
Thank you, Dan. Thanks for answering the question on form. Richard or Steve, have you questions for Dan? Let's not do the econo-bashing quite yet. Let's understand what the model that Dan has presented. Richard, go ahead.
I have 2 concerns. One is just a point of information. And that is then when you say that economists assume that dy dt is 0, that is just not true, right? And particularly Nordhaus has never claimed it is 0, right?
We absolutely did, Richard.
No, sorry, Dan, I think you just misread those papers.
I don't think so.
But then with regard to your contribution, essentially what you say, well, the pattern of development has been constant for the last 150 years. And therefore, the only thing that we need to explain is that pattern. And then essentially what you do is you run a regression of the initial conditions in 1820 on the temperature, and you find that the slope is, I believe, 6.9, is what I think you found. And that is essentially what you did, right? You just ran a regression, a naive regression of the pattern of affluence or the pattern of per capita income, whatever you want to call it, on temperature. And that is your whole story. And that sort of, it's historically inaccurate, right? We've seen countries catch up, and the question is really, why did some countries develop before others? An interesting question that Douglas North and colleagues raised is, of course, why do some countries grow and other countries grow and shrink and grow and shrink and grow and shrink? That's an interesting question. But really the question here is what countries developed first and why, and does climate have anything to do with that? What countries developed later? Is this a catch-up process, or does climate have something to do with it? And of course, the more important question is, why did some countries not catch up, right? Whereas, of course, we should also realize that particularly East and Southeast Asia, and now South Asia as well, are very rapidly catching up despite being in very hot places. And that is, I think, the more interesting question and the more relevant question, because it sort of brings institutions back into the picture. It brings human agency back into the picture. It brings colonialism back into the picture, and so on and so forth. And a simple regression of, simple in the technical sense of the term, of per capita income on temperature, I think doesn't tell us anything interesting, A, but B is sort of completely the wrong place to start to talk about what would be the implications of an increase in temperature, what would be an implication of climate change. Sorry, I just don't see what you've done or why it would be interesting or useful then.
Well, what I've done is I've created a dynamical system that predicts this stable, long-term stability. And, you know, we made a prediction, we tested it, it's there. So, you know, that's pretty much the standard. And we can put colonialism in. In fact, we put colonialism in. You know, first mover advantage, if someone wants to put in first mover advantage, well, I'd like to know how to do that, or I'd like to see someone construct a dynamical theory that puts that in and shows that it's important. We put in social norms, we put everything in, we test everything under the sun. And so, you know, the notion that it's what you call a simple regression is not, it's a regression conditioned by a dynamical system. It's the only regression, we only use regressions which are permitted by the dynamical system. And that's really the fundamental problem with Acemoglu and others. They regress against variables which are really output variables, and therefore they get very high correlations, and they don't see the things that are really there. Period.
So Richard, do you want to pick up on that, or can I move on to the next question?
I can expand on that, right? I mean, the idea of constancy is just not there, right?
Look at it, it's there.
If you take a deeper dive, in economic history, then it was the Fertile Crescent that got rich first, right?
Sorry, say that again.
It was the Fertile Crescent that got rich before everybody else. It was Southern Europe that was much richer in historical times than Northern Europe as it is now. Around the turn of the 19th century, not Australia, Argentina was the richest country, one of the richest countries on the planet, right? And it sort of never got out of that. Sort of has been stagnant ever since. You can look at Bangladesh, for instance, that yes, fitted 15 years ago this story of tropical poverty, but doesn't anymore, and so on and so forth. You can look at the island of Hispaniola, right, which has the same climate, but one half is one of the poorest countries in the world, and the other half is a middle-income country by now, and so on and so forth. Same for the Korean peninsula, right? So the story is simply incomplete, but at the end of the day, what you do is just say, well, the pattern of rich and poor today depends on the pattern of rich and poor in 1870. I misspoke, I said 1820 first. And essentially we can run the pattern of who is rich and poor, we can run that on temperature, and that explains the pattern. Of course, it does in the econometric sense of the word, but I just don't think this is how we understand economic development to work. It's essentially, you go back to climate determinism, which I had hoped Lucien Lefebvre had actually buried in the 19th century, but apparently is rearing its head again, including in academia. And I'm just very surprised by this, and that may, I don't know whether there's any historians of economic thought or historians of science who are listening to this. It is an interesting thing that this belief that people used to have, going back all the way to Bonzong, right? That is still alive, even though it has been sort of shown wrong time and time and time again.
Actually, it hasn't been shown wrong. The claims have been made time and time and time again. And Nordhaus is very clear about that. He says, up until the 1950s, we used to believe one thing and now we shifted. But in fact, there hasn't been very much debate about why the shift. There has been no, I would say, no critical evaluation of it at all. And really what we have is two competing schools. And what we need is to translate those two schools into a language which is the standard for scientific discussion, and that is differential equations. And if you can't put it into differential equations, you got nothing. You got nothing. And I've put this into differential equations. I didn't prejudge it. There's nothing in the theory that says it's going to turn out one way or the other. Well, I just put in the phenomena. I took North's prose, I took Williamson's observations, I cast it in differential equations because they were not able to. I coupled them in a way Solo wasn't able to, and you get this. This is predicted, okay? And this is, I don't know what you're talking about when you say it's not constant. Look at it. It's constant. And yes, there are exceptions. I heard it from Joel Molkier recently. Oh, well, you know, it works and works and works, except when it doesn't. Well, that's the whole point. Science is full of most things being mostly true, and there's exceptions, and you got to deal with them. Yeah, okay, we got to deal with a few things. We understand that. But actually, what's happened, the exceptions are things coming close to where this argument says they should be. Anyway.
I'm just going to interject and say we've got potential for an interesting debate. If it goes to the conclusions and sort of gets personal, it's not going to be interesting. So I'd like to highlight some themes that I'm hoping we could kind of keep our comments to. So there is a long run narrative about determinism, you know, which you highlighted, Richard, in your, you know, your abstract, you know, a general Malthusian approach, you know, of doom, which perpetuates lots of disciplines in social science. I think it would be interesting to get different perspectives on that. There is the question of, I haven't put these down in any particular order. There is the question of volatility and bounds and how those issues are dealt with by the models and the modeling, the theories and modeling around, you know, how we conceptualize these things in data and in predictions. There's a fundamental question of method. And then there's, you know, economists' predictions and how they have been done. Obviously, there's a really patchy record in that regard, but it might be useful to clarify some of the basics, like the Nordhaus meant zero. You know, like so there could be some useful stuff on clarifications on that. Dan, I have one question that I want to ask about your work. And I'm going to use chair's privilege to do that.
Yes.
And it's a question directed at you and the other panelists. And that is, what I see you doing in this paper is trying to create a dynamical system that makes assumptions about different phenomena. One, the climate or natural phenomena, and the other, the human production stuff, the economic stuff. And what you have is a dynamical interaction between them with, you know, lags and processes and investments and all that kind of stuff. To what extent do you, regardless of whether, and I think there is an issue around, I mean, I know as a historian that lots of your data sets are smoothed. And so they are covering up the exact, you know, issues that Richard is highlighting as being much more stochastic than we think. But regardless of what data sets go into them, I would like to know whether you thought that with better or different data, what the contribution of interreacting human production and natural phenomena is. And I would like comments from the other panelists on whether that has an approach in, you know, that is anyway novel or different, and whether it can overcome the issues of measuring volatility, method, and determinism that seem to bug this debate. So I'll leave you go, or whoever wants to go first on this one in case I've floored you. Daniela, you're mute.
I want to complicate the question that you are asking a little bit. And I don't know, it might be a naive question, but when people speak about climate change today, sometimes they say we shouldn't be speaking about climate change. We should be speaking about the global crisis, which includes climate change, environmental degradation, extinction crisis, and so on. And the question I think needs to be asked is when we're looking at the impact of the climate change, and we're saying, okay, like such and such change in temperature is likely to lead to 10 or 5 or 3 or 20% lower GDP or like Human Development Index and I mean, the environmental degradation issue is not directly related to climate, and there is a lot of things. There are a lot of things like overfishing and soil erosion and forests being cut down. So if we actually put this all together, what kind of picture are we getting, and what has been done by economists such as Nordhaus, for example, to answer that question? Because I think when we're looking at 2050 and asking ourselves, like, what life is going to be then, it makes no sense to look at the climate in isolation, because environmental issues are not going anywhere. They will affect this as well.
Do you want to respond, Dan?
I don't, because I don't feel qualified to respond. You know, it's just in that other realm of how, you know, there, as I said, there are two terms. How do economies change when sort of the facts on the ground change? That's really the question you're asking. And then it's plus, how does the economy change when the facts on the ground are constant and it's just the temperature? That's the piece that I can address. The other part is, you know, I won't say that no one can do it. I just haven't thought about how to do it. I know it's important. Okay. I just haven't thought about it.
It's not just important. It's like important with a huge capital I.
Yeah.
And I don't dispute that for a second. I don't dispute it. I will just you know, it's a harder problem. It's just got a lot more subjectivity to it, for one thing. I think Richard Toll made some, made some excellent points about human adaptation. We adapt, okay? And so we can adapt to things. Freud talked about how we can adapt. We adapt, we make tools. It's what the world is going to look like after we have adapted to it. I don't know. What we have, to me, the evidence is, Arrhenius says 7.2%. We show, but we humans in the 21st century can show only 4.2%. Okay, we've reduced, we've adapted to nature by taking away 40% of its penalty. Okay, when we're going to adapt in other ways. So I don't know what the next technology is going to be. Okay, but I'm going to bet on humans adapting. I'm going to whatever extent possible. But the geophysics, that's one thing. And the second thing is, where are their cliffs? I don't think the response of the Earth is going to be linear. But what I say on this matter means nothing. What Michael Oppenheimer says, or what Richard Toll says, or maybe Steve Keen says, those are people who've looked at it, and they can tell you something about these circulations, and I can't.
So can I invite Steve? Steve, have you got anything to say on the question of this? First of all, I can feel that you might make the comment that, sure, we can adapt, but, given that we have choices, you know what I mean, what we have to adapt to can be mitigated. So I'm wondering whether you would care to comment on what Dan had to say about the interactions of production and climate, and whether you have a comment on the kind of linearity methodological point that he's making.
Firstly, I apologize. My microphone's likely to be dreadful because my other one ran out of battery power. I'm trying to recharge it right now. So the sound, I take it, is awful.
Thank you for saying so.
Okay, sorry about that. What I'm saying is a comment about adaptability to a physical distribution of climates on the surface of the planet, without considering what happens when we dramatically increase the amount of energy retained on the planet. And that is the danger, that one of the reasons we became so adaptable is for the last 10,000 years, the climate was incredibly stable. There was a variation of not much more than 1 degree either way, up and down. And there's a 10,000-year period in the time series of the temperature of the planet. If you take a look at that against the previous 800,000 years, there's no period like it. So one of the reasons why we evolved sedentary societies was we had this period of extreme stability of the climate. Now, we are destabilizing that at a ludicrous rate to a level which hasn't been experienced, if we keep the current trends up, for 40 million years. And when we do that, it's quite likely most of the life forms that have evolved to live within the climate of the Holocene and the previous 800,000 years of relativity, we're blowing right outside their range. So we are setting forth a whole range of biological and biophysical processes that we do not understand. The scientists are closest to understand it, and most of them are terrified. I'll give you one example, which is a bit of an old one, and it's not being backed up by a lot of subsequent research, but it's nonetheless in the literature. And that is that we know that the planets are warming unevenly. So the average change in temperature is about 1.3 degrees by now. The poles rising at 5 times the average, the equators rising at about half the average. James Anderson, who's the man who discovered the hole in the ozone layer and led the campaign to address it, argues that if we lose the Arctic summer sea ice, which is the first of the 8 tipping points that are considered in that Deeks paper, if that one alone goes, then he says essentially the temperature difference will disappear. Now that could mean, for example, we go from 3 circulation cells in the Northern Hemisphere to 1. That has got all sorts of potential ramifications. It could turn the middle 20 to 70 degree region effectively into a desert, which would be very hard to adapt to. If we move to the regions where there's rainfall, there will be no topsoil, which would make it rather difficult. That he also said would lead to a leakage of moisture into the stratosphere. The moisture will contain CFCs, and chlorine and bromine, which will break down the ozone layer, and that could eliminate the ozone layer. Now, we don't know whether he's right or wrong about the scale of it, but that one's potential danger that if the ozone layer goes, then effectively there's any form of life out. And that for means we need to survive in indoor agriculture. Well, that will be fun. So yes, shake your head, Richard. I think I'll take far more notice of Anderson than I'll take of you.
I think he's
This is a major danger, and we
Yeah.
are playing with it, and that's what I'm really scared about. By the way, the
Thank you,
economists
Steve.
approach
I'm going to capture that. Richard has a PhD student in a couple of minutes, so I'm just going to get his
That's
response to
that,
that
yeah.
before he moves on. Thank you, Richard.
No, I don't think I have anything to add to what I've already said. So
Okay.
it was a pleasure to be here.
Thank you.
Thank you so
Thank
much for
you very
coming and
much.
for your contributions. Really much appreciated. Thank you. Okay, he's off to a PhD student. So Steve and Daniela, and Dan, do you want to respond to what Steve's saying? Or does Daniela have a comment, or would you like to respond to the kind of framework I offered earlier?
No, I think, no, I there was just Richard and Steve were misreading each other. That's all.
Which, yeah, can happen. So, but there was another issue. Do you think that was the point that Steve was making was in relation to Richard, or in relation to what
No,
you
Richard, no, it's, we'd surprise no one and reveal any great secrets by saying that Richard and Steve have some longer term conflict. Okay. Nobody, they both admit it. It's obvious. No, I'm not complaining about it. But Richard was shaking his head in response to your query, Judy, about do you have something else to say? And Steve,
okay.
not being aware of that in the chat, thought that Richard was disgusted with what Steve had to say.
Oh,
And
no.
that wasn't what it was about. So that's all I was trying to say.
Yeah, exactly. That was established. His diary was not. Okay. Do you, I mean, could I actually ask you, Steve, about, since we're sort of into discussion time, what do you make, because you are very well versed in the history of economic thought. What determinism has, you know, the kind of like, so as an economic historian, I deal with a lot of determinism around labor, poverty, and determinism also around gender, biological determinism and human capital theory, all this kind of stuff. And a lot of it is based on classical and neoclassical assumptions about, you know, how, you know, curves interact, about how supply and demand will interact and, you know, lead us down a marginal route of, you know, never-ending misery. What role, if we move away from the kind of the econometrics and the cleometrics, what role does a deterministic view of the world have in climate debate, or the debate about how we mitigate the effects of our previous actions, from your perspective?
I think, again, I see Richard's framing of this as being convincing and utterly inappropriate at the same time, because what he's saying by climate determinism is that the climate you experience on the surface of the planet is not a major determinant of whether you be economically successful. So we have Singapore with a hot climate and highly successful, Indonesia right nearby with a hot climate, relatively unsuccessful. And then you have, as he's saying, in that sense, climate is not a major determinant of income. That's the proposition he's made all the time. That's got nothing to do with the climatic context in which human civilization has evolved. And the fact that we have sedentary systems that enable us to build, first of all, agricultural and then industrial civilizations, is something which is in the background. And so long as that exists, his statement is true. The trouble is what we're doing by climate change is destroying that stability, at which point we could easily have a complete breakdown in the capacity of the agricultural and manufacturing systems we have to enable civilization to exist. And then we will now have a new form of climate determinism. The climate will determine human civilization can't survive. And the flippancy with which mainstream economists approach their work on this has left me completely flabbergasted, Judy. I mean, you know, I've read decades of reading neoclassical economics. And when I went into reading this stuff first time around, what I expected to find was that they'd taken the work of the scientists and then applied a large discount rate. Most of my colleagues in heterodox economics had that belief. Most of them can't stomach reading neoclassical economics. I don't blame them, but I forced myself. Anyway, I read it, and what I found instead, they'd made up their own empirical relationships. They'd said that the current GDP and temperature relationship can predict the impact of climate change, which is nonsense. They assumed, I'm just sort of left speechless by half the things that I read, but they assumed that anything done indoors would not be affected by climate change. Now, close-free controlled environments. That was said by Nordhaus in 1991. It was repeated by Toll in 2014 in the IPCC report. This is fundamentally making the mistake that Richard himself pointed out, of mistaking climate for weather. Now, all their empirical studies have looked at weather-exposed industries. They haven't looked at manufacturing and services. And again, the ignorance here is just breathtaking. And partly it's a general ignorance coming out of neoclassical economics. But it's also a special level of ignorance within the climate discipline itself. And just to give you an example of that, they use what they call the Cobb-Douglas production function. You're probably familiar with that, which is output. Okay, output is a function of technology, which is A times labor to raise to a 1 minus alpha times K to raise to the alpha. And that's what they fit their data to. Now, that has no role for energy.
Yeah.
Now, when I've brought in and said, well, energy, without energy, labor is a corpse and capital is a sculpture. So when you bring that in, the energy input to machinery, rather than having the energy having a coefficient of 0.03, which is what they use when they simply tack it on as another factor of production, it becomes a coefficient of 0.3, 10 times as high. Then when you look at cross-country data, to fit the data, you need to make a coefficient of 0.8. This is something that Gregory Mankiw said back in 95. It's not being a radical to point that out. And what that means is there's an incredible dependence upon manufacturing and all other industries that take place in carefully controlled environments on an energy supply. Now, we get our energy from fossil fuels. If we find that we are destroying the livability of the planet by increasing the temperature, and we're falling right into that range right now, then at some point a political decision will have to be made, stop using fossil fuels. If we do that, there'll be an 80% fall in the energy input we can put into manufacturing, which implies an 80% fall in manufacturing or better. Now, Nordhaus, writing in 1991, and he hasn't changed his thinking one iota since then, said that it's very hard to find any way that climate change will affect manufacturing over the next 50 to 75 years. Okay, it's a blistering level of ignorance. And the trouble is, this is ignorance about the most important issue humanity's ever faced. And that's why I'm so angry.
Yeah, no, fair enough. To be honest, and I'm very glad he's not on this call because, as you say, he hasn't changed the opinion, whereas everybody else who has been on this call has shown like a level of granularity and adaptability that makes things a little bit easier to deal with. So that helps.
Nordhaus was invited, by the way.
Yeah.
Oh, well, that would have been real fun.
And so is Asimoglu, and so is Robinson, and so is Melissa Dell. And they all responded politely.
Well, that's good. Specifically, Steve, because of what you were talking about in relation to tipping points.
Yeah.
And the bulk of what you presented today, I know you've written other stuff elsewhere, but the bulk of what you presented today is about natural phenomena, not social phenomena. So it's about the way that, that carbon-based fossil fuels behave when burnt, and it's about what happens to natural systems, that are affected by the dynamic forces of, the interrelations of physical properties on the planet. Yeah. If those things are to some degree with obviously with some huge time lag beyond our control, you know, in the longer run within our powers, but maybe not control. But if those things in the short run are beyond our control, what are the aspects of, or what, you know, what are the approaches to the social side of things, i.e. the production stuff, that we should be looking at? I mean, you spent a lot of time on this, as you say, a cut in fossil fuels. You know, that was 1991. That hasn't happened. So what are the adaptabilities? Because adaptability, technology, innovation, these things, you know, are part of human history. What are the things we should be, what are the unanswered questions from your point of view about how the adaptable process in social phenomena will affect things or should affect things?
Well, if we'd done this 50 years ago, this would be a polite conversation. It would be easy. And Nordhaus, as you know, was the one who demolished the credibility of limits to growth without understanding the technology underlying it.
Sorry,
so we didn't.
Steve,
Yeah?
I am having a little bit of trouble through that microphone. If I could ask you to speak a little slower.
I'm sorry. This is really bad.
Just speak a little slower.
I will. Yeah, sorry.
All the syllables will come through.
Adele is a dreadful.
Just go back
powerful,
2 sentences.
Yeah, I've got a powerful theatre with very dreadful sound system. So this thing, I'm hoping it'll recharge in time, but no luck so far. Okay. If we had started adaptation 50 years ago, which was the argument of the limits to growth, then we could have done it in a smooth fashion. Instead, we've delayed it for 1/2 a century. And in that half century, our load on the planet has trebled at least. And we've pushed the temperature level up by at least 2/3 of 3/4 of a degree Celsius. So we're already pushing our boundaries. And so when you're talking about adaptation, it's adaptation in the context of climate breakdown. Now, if that climate breakdown has some of the elements that some of the scientists I'm in regular contact with are expecting, and that's such things as the collapse of the AMOC, for example, and therefore wiping out 80% of the planet's capacity to produce wheat, then we're going to be forced to ration basic foodstuffs. Okay. If you imagine what would happen to the population of the planet if that prediction is correct, if the AMOC does collapse, and if that, rather than causing an increase in GDP, as Richard's paper dreamt up, instead causes an 80% fall in wheat output, then there will be riots, food riots. And the only way to survive is going to be enforced rationing. That's the sort of adaptation I think we face.
Totally. I've got a lot on food riots at the moment in the 1780s. My one question then is, what is the time period that we should be looking at? You know, because like Dan has decadal data. And, you know, the 1780s look lovely in 1781, and they look okay in 1799, 91. It's just the 10 years in between that was really hideous. So what are the time periods that we should be, or the lags that we should be looking at when we look at data?
Well, in terms of the time period, I think rather than the type of far future stuff that Richard argues we face, anybody who worries about climate change is concerned about the far future. I think anybody who's concerned about climate change is worried about the next 20 years. That's where we're likely to see the impacts hitting. And the time lags, unfortunately, are of the order of decades in terms of once you put carbon dioxide in the atmosphere, then it takes up to 100 years for that molecule to come back down and be put back into the soil again by plants and so on. So we have set up a system which there are enormous lags in the response of the climate to what we've pumped into it over a period of 120 years, but really with the amount of carbon dioxide in the atmosphere has risen. Most of the rise, of course, about 80% of it's been in the last 50 years. So we will face consequences of up to a century if we remain in control of the processes. And if we don't remain in control of the processes, then if we do get, even without the runaway climate change breakdowns, we could be facing 2 or 3 centuries to bring it back to the stage where we have something resembling a Holocene climate. The worry that climate scientists have is that things like the permafrost going, which contains far more carbon than we've pumped into the atmosphere already. Ocean methane hydrates, which are even scarier. If that amount of carbon gets into circulation, then we're talking millions of years to get it back down using natural processes to something like the range in which the human species evolved. So we're playing with enormous forces, and it's the cavalier way that economists have approached this that I find the most terrifying thing, because I think they started from the position that capitalism can cope with anything. It's the most flexible social system ever. Therefore, climate change can't be a problem. And they then went about proving it by making up the numbers to reach that conclusion.
I'm not going to disagree with you about that narrative, because I think that there are a lot of people who drank that Kool-Aid and who shared it around. You know what I mean? Who drove the punch bowl of it. Dan.
Yeah, I'd just like to say a little bit about the timescales. So, with regard to my work, the time scale is not determined by the data. The time scale is determined by the phenomena and the rates at which things change and fall apart. Those, I'm just going to put this slide up again. What Ann and I showed, is we described a driven linear dissipative system whose timescale is set by the useful lifetime of roads. That is, and the reason it's the useful lifetime of roads, roads are economically productive capital improvements. I mean, they're economically productive capital, or what we call capital improvements and it's been known for a long time that they're hugely economically productive. So given that they're so important, the time scale of their decay turns out to be dominate the whole dynamical system. It's the time scale for the decay of the most productive capital improvements. That's what governs the time scale. So, whether you call that a decade or 2 decades, something like that, it's in that range. That's the time scale. Now, I don't have data every year. I have data every year between 1990 and the present, but I only have data going back 150 years. It shows that things are approximately, I'm just going to go back to this, stuff is constant. It just is. It's not, I didn't make this up. It's just there. So it's dominated by constancy. And so whatever is driving the economy, that is, these differences are driven by things which are constant on a different time scale. But getting back to the climate issues, things are happening on longer time scales, exactly as Steve mentioned. And so if we keep pumping heat into the ocean, well, the ocean hasn't thermalized. The time scale for that is thousands of years.
Yeah.
So we put this heat in, we're going to be coping with it for a long time. And with respect to your point, how fast can a shock happen? Shocks can happen fast.
I'll agree. Shocks can happen fast. Responses take time. Steve, do you want to respond, or Daniela, have you anything to say? Actually, it'd be nice to get. Oh, you got to go right back. Okay, cool. Sorry. And you were gone, and now you're back. Thank you. Sorry, I didn't understand that. My Zoom lingo obviously isn't up to this.
It's from 1990s.
That's why I should know. I really should. Do you want to respond to this question of constancy, from a technical point of view before we go back to Steve? Because if you were looking at this dynamical, data-driven rather than theory-driven model, does the question of constancy have something, is that something you can deal with? I mean, this comes up as an economic historian. This is about aggregation and about general statistical approaches, because we will always get a constant in the long run, and you will get convergence in the long run once you start indexing anything. I mean, it's the Pash problem. So is that something that you would like to respond to in your kind of data responsive approach, or do you have another question for particularly Dan or the discussion as a whole? Or shall I return to? Is constancy something like the problem that in the short run? Okay, so here's the problem. One of the problems, and it relates to finance and financial systems, which Steve knows. So between 1982 and 2007, the world's developed economies experienced this, what Ben Bernanke calls the Great Moderation. And you can plot, what we mean by the Great Moderation is that interest rates normalized and output volatility, the output of production in the economy, came right down. So volatility shrank to, what we all have experienced, what we perceive as normal over the last 50 years. That moderation became the model for a great deal of economic planning, tools, and theory that was then applied to, you name it. And so there was a golden age of labor, through collective wage bargaining, 45 to 75, which provided a whole pile of theories and models for labor econometrics. Before that, are there data-driven systems that can cope with the fact that the paradigm of particular eras, determines how we view things, or do we need the theory that Dan is talking about?
Well, somebody who modeled the Great Moderation before it happened, I think we need theory. What we call the Great Moderation, from my point of view, was the decline in the. It's actually part of a chaotic process known as the Hameau-Maneville route to chaos, which came out of my model of Minsky when I built it in 1992, which is several years before the neoclassicals invented the term of the Great Moderation. So again, that's a classic case where their equilibrium orientation led them astray. They saw that decline in volatility as a good thing. I saw it and thought, holy shit, this model that I thought was only hypothetical is actually turning up in the data. And that model predicts a breakdown will occur if this trend of diminishing volatility actually persists, which is what happened. So I think there's so much in mainstream economics which doesn't understand a complex interacting system. And that's why I very much agreed with Daniela's arguments. We need a system dynamics approach to understand the system which we're in. And one reason economists don't is they don't have system dynamics, they have equilibrium modeling still. And of course, they drove the limits to growth out. And I know from speaking to Randers, one of the authors, that they really thought economists would welcome the technology of the limits to growth because it would free them from having to think in equilibrium terms. And they were horrified when they were basically attacked and tar and feathered and driven out of town. Now, I think it's time we tar and feather the economists instead and brought system dynamics back in control of how economics thinks.
Can I make a point here? Maybe did you want to say something, Daniela, in response to Steve? And because if so, I'll wait.
No, I just want to raise my hands or because what he's saying is ridiculous, frankly, but that's what happened.
So
Dan, come in. Okay, so
it's quite entertaining to have the three of you in conversation like this.
It was, yeah.
It took
Very.
a lot of effort to make this happen. We ought to do it more often and more casually so that it may, you know,
Agree. Yeah.
because we could understand more. And, you know, I knew Richard was going to take a different point of view, but it was important for him to be here. We should have other people, but nevertheless, equilibrium. I'd like to both make a point and ask a question about equilibrium, because what the data says, it seems what my dynamical system says is that there is constancy, which is one form of equilibrium, and there is simultaneously growth. So we are not, so the equilibrium that exists says nothing at all about the ability of the economy to grow effectively with no bound in sight.
Yeah.
No bound in sight. And yet the relative positions of these countries is in a state of equilibrium. Okay. Those are two, I mean, it is a fact, the relative position of those countries.
Getting something graphic. Oh yeah.
So the relative position, and I mean, if you look at that, the relative position is fixed. I mean, is there. If I stretch the thing with, you know, technology, the positions don't change. The relative positions don't change. I've just changed the scale. That's what technology is doing. It's changing the scale, and the wherewithal of any country, any nation, to incorporate the technology that is coming. You know, much intellectual property was invented in the United States and it ends up in China. So stuff moves. If anything moves in the world, ideas move faster, right? Ideas move almost at the speed of light, okay? Boats slower, but technology can move, the ideas can move at the speed of light. And so the ability to pick them up and use them determines where you are on this chart. And as the, okay, now some things, and all I'm saying is that temperature, because it at the very least is a leak, is going to play a part. That's all that says. And if you, so, but the constancy says we don't need complex dynamical systems to understand it. It's not chaotic in the long term. Maybe all these little wrinkles, if I can.
Okay.
So maybe the wrinkles are chaos. I don't know, but the wrinkles are noise. The wrinkles are all kinds of things. But the constancy of it does not want complex dynamical systems.
Actually, on that front, Dan, so you've seen the work of Tim Garrett.
Unfamiliar, I apologize, but I don't know.
Okay. Look for Tim Garrett's work, because he's done a very similar thing to you in that sense. But what he's actually done is use thermodynamics to derive a constant relationship between energy and wealth. So not GDP, but the integral of GDP, and finds quite a long-term constant relationship there. Now, I work in the short term, and I build dynamic models that have cycles between change in energy and change in GDP. So that may be the only sensible definition of the long run that I've seen. But when you take a look on the grand scale at thermodynamic levels, then you don't need the short-term cycles, chaotic behavior at all. And that's similar to what you're getting out of your work. But he finds a constant relationship between change in wealth or growth in wealth and energy consumption. And it's a very, very strong constant over the last 70 years. So look for Tim Garrett's work.
Yeah, I wouldn't doubt that at all. There's a whole bunch of, so, you know, Judy will say well, anyway, so this, the correlation between the energy use and the wealth is no surprise. Just like the correlation between education and wealth, the correlation, it's just all those things, that energy use, that co-evolves. And when you put that into the dynamics, you'll find that the things that co-evolve are all highly correlated. And when you look at the proper eigenvector of the economy is not GDP. It's GDP plus economically productive assets.
Yeah.
Which,
okay. Yeah.
Okay. And so it's not exactly the integral, it's the integral, it's the solution. Well, the integral is the solution. One way to use the word integral is as a solution to the differential equation. But you can't just integrate this thing up. You got to take care of the decay. Stuff is falling apart.
That's what's coming out of Tim's work as well, because fundamentally it's saying most of what we call GDP is actually energy being input to maintain the structures we've built over millennia that are the basis of civilization. So
well, from a construction point of view, absolutely, yes, concrete.
Yeah, I think you take a look at that, Judy. You find it interesting.
Yeah, no, it's on a reading list here at the bar.
Yeah.
Absolutely. Yeah. So the maintenance of core structures accounts for a massive part. Sorry, Dan, Daniela wanted to come in on the point that Dan was making before.
Yeah, I wanted to comment on Dan's criticism of the complexity and the unpredictability thesis. I think no one is making the point that we need to use chaos theory or something fancy like this to understand the basic processes of like adding CO2 to atmosphere and heating the planet, etc. Where I think simulations and system dynamics models can be extremely important is when you are facing a transition. For example, a transition from a working civilization to a dead civilization or something like this. Because here, different processes might actually play out in very different ways, and scenarios can be very different. And here you can't just presume constancy in, for example, relative positions, because like when billions of people, for example, when billions of people start dying from hunger, it will be important in which country climate change will cause famine first. Because it might happen in India and then you will have 1 billion people dead there, or it might happen in South America and then you will have something in Argentina or in Brazil. So I think the reason why I'm interested, for example, in system dynamics models and extended multi-method models is that we are apparently getting close to a transition, or at least that's a very real possibility. I mean, like 99% likely possibility, transition of some sort. And so it is important to understand like what will break first, what do we need to fix first, what will happen if we fix that part but not another part. And I'm not saying anything about chaotic nature of these processes during the regular growth phase when the economy develops normally. Because when you look at the graphs that, of relative positions of the countries, that all happened after the start of the Industrial Revolution, when we had access to cheap energy, coal, oil, gas, and obviously everyone was trying to grow as much as possible. Some countries managed to do it a little bit better. For example, when Soviet Union decided to implement a planned economy, for some reason, for some time, it managed to grow much faster. And of course, other countries could not copy it because it was ideologically wrong. So it got a head start. And then at some point, Japan managed to grow faster for some other reasons. So there are some differences, but in general, yes, the process happened at the same speed everywhere, more or less, or at least in the same direction. But that was when you had abundant energy. Now, when that condition is ending, it's extremely interesting, and also I would say it's extremely valuable from a political and geopolitical and corporate point of view to actually understand what are the options, because you can play those and I mean, you can get an advantage if you understand potential trajectories better than others. Like, for example, if New Zealand understands how climate change will unfold better than Australia, it will get a huge advantage, and vice versa.
Okay, so I would like to answer in the affirmative. What you are saying, I think, is that you need chaos theory for chaotic circumstances, right?
Yeah.
Double thumbs up. Absolutely. This stuff that I'm talking about says nothing about, say, chaotic circumstances, and you're talking about all the scenario planning and you know, trying to figure out how to deal with that. I'm not even going to call. I don't know if it's a shock or a transient. They're different, but let's at least call it. And it's not even a transient, which with that discontinuity, that's what it amounts to. If it happens over something like 15 or 20 years, anyway, it's good throw this discontinuity. So that's what you're saying. Absolutely, I see the value of that there. I don't think, though, by the way, that these guys here back in, you know, in Santa Fe are talking about that. They're you know, they're a bunch of smart guys, but they didn't look at the data. And you know, you found me, and I still don't think we have found the best way to bring our two understandings together to say something that'll be really valuable to others. We got to figure that out, you know, and maybe there's, you know, there are 4 really different kinds of views here with enough sympathies to, you know, be able to talk.
The other thing that's interesting or important is that the questions are now evolving at a faster pace. As Steve was saying, you know, well, essentially, Steve, you were saying, I wouldn't start from here. I would have started 50 years ago when the problem became apparent. But now that we are here, the question is slightly different, because it becomes less about can we stop and more about adaptation systems. And also it becomes about what the political and social ramifications now need to be adjusted as. I think it was the chief exec of Aramco, can't remember his name, sorry for being unprepared, up in the FT the other day is saying, like, anyone who doesn't think the carbon transition is going to be a riot has got the wrong end of the stick. You know, we all understand what needs to be done, you know what I mean? But, you know, you're all thinking we can do this smoothly. You know what I mean? He actually showed he had some grip on history and that he knew these things weren't smooth. Well, I'm not particularly keen on the stuff that his company is in, or, you know, lots of stuff where he's coming from, but they were some very wise words for the chief exec of an organization like that. And the reflexivity of these questions, how they are dealt with, is becomes an issue as well. And this is where measurement and modeling really have a contribution and traction, right now. So Steve, could I ask you a question about, is there a case, like, let's get away from the modeling thing for a minute, and let's or the long-term dynamics. Is there a case that we should study? Should we look at something panel-wise?
No.
For rapid change?
I think we just accept what the science told us. Let the temperature get past 1.5 degrees above.
Okay.
And work out how to finance that. It's really coming down to how do we pay for, and then how do we build a transition from a carbon-based economy. And if we don't do it before we hit 1.5, then we may not be able to do anything about it after we break 1.5. That's the real point about tipping points. And 1.5 itself may be too high an estimate. We already know it's quite likely we're going to lose summer sea ice in the next 1 or 2 decades. And when that goes,